2025 itself. He completed his PhD at International Center for Theoretical Sciences, ICTS, followed by postdoctoral research at Max Planck Institute of Gravitational Physics in Potsdam, and later at the University of California, Santa Barbara. His research interests lie in gravitational wave astrophysics, gravitational wave lensing, and using GW observations as a tool to test general relativity. Please join me in welcoming Professor Ajit.
Thank you, Nidhi, for the introduction. And I don't know, I don't see Chandra and Arun, but yeah, I want to thank Chandra and Arun also for, of course, this is very special moment because it's exactly 10 years since the time when first detection happened actually. So yes, at that time I had just joined PhD student. I didn't know that such a big thing will happen. But anyway, so as I mentioned, I don't know, the laser pointer is not working. Anyway, so as you can see that, so I've been asked basically to give you an overview basically or summary of all the physical results that we have derived from LIGO, Virgo, Kagra detector data. So of course it's really difficult job to give you a summary of all these results in just 1 hour, but okay, I hope at the end of talk you will have some feeling of the range of physics and astrophysics that we can do with gravitational-wave astronomy. I mean, it is like I don't need to remind you that gravitational waves, because you have heard 2 talks now that gravitational waves have opened a new window onto the universe. Any time when a new window is opened, right, you get new information. For example, the discovery of radio, electromagnetic wave changed the way we look at the universe, right? Before that, we just saw the galaxy in our images based on our eyes in the optical range. So similarly, if you open a new window, definitely you get new information, and what I am going to tell you is that gravitational waves gives you a whole lot of information which is very, very complementary and new compared to the electromagnetic spectrum. So some just in one slide, I wanted to give you some summary, for example, of how do we detect gravitational wave, which I will not discuss, but it's a very interesting part of data analysis, tool that goes into this. But my talk will start. Let me. Not working. No problem. So sorry. So generally in this part of the talk, I don't know, something is happening. It's ringing. Just one click, right? Long press means. Yeah, but one. Okay, sorry. So I hope. Okay, I will keep that in mind. Okay, so generally, you also heard Sri Ram's talk, right? So there are various sources for gravitational signals that produces signals in different frequency bands, and but those are, some of them are far in the future to be detected. So let's not talk about that. I am going to talk about all the results that we have detected basically based on this ground-based LIGO Virgo detector. So we have the data. How do we extract information from it? In a very summary basically. So you have a source of this kind. Very I would say that this is very clean problem. in general relativity compared to the cases. So everything whenever I say it's related to something, it's not at all a easy problem, but it's easier problem than, let's say, if you want to try to solve two compact objects in binary when it's not black hole. They are not black hole. They are like, let's say, they could be some exotic systems, or let's say neutron star. Whenever there is matter, it becomes bit more difficult. But let's say you focus on two compact objects, could be black hole and neutron star or whatsoever, and they are far away from each other. They are parameterized by, let's say, masses m1, m2, and spins, and as you can see, the details are not very important here. So you have some source, and the properties or the parameters of the source is given. Then they will emit some gravitational signal. This will get recorded by the LIGO Virgo. Let's say, for example, a particular LIGO observatory placed in Livingston, and this basically outputs some time series that looks like very, if you just look at it by eye, it will just look at random numbers, right? So, but the job of then the data analysis people or basically is to uncover or discover basically gravitational signals. If they could be like buried into this, they may not be, right? So then is this thing, let's say there is a black box where you just feed in this data, and then if there are gravitational signals, that black box basically will give you the signals, and that black box is called search pipeline. I will not go into the details, but my talk starts from here. When, let's say, we have extracted the signal confidently, what can we do now? Okay, and of course, in this whole basically long of the data, right, the signals could be just buried into just, I guess Arun must have discussed it. It could be just like, if it is really massive binary, it could be just 0.1 second, right, and if it is binary neutron star, it could be hundreds of seconds, right. So yeah, as I hope I understood what I am going to, what would be the aim of my talk. So I will just start from the fact that we have extracted signals, but of course, when I say that extracted signal means I do not just extract this part, still you have, that in this chunk of the data, you have a signal, but there will also be noise, right. So that basically leads to measurement and sensitivity, etc. But we know that at this part of the signal, in this part of the data, we have signal, and there are tools by which you can measure the parameters, etc. And from there, what we do basically, this is the aim of the talk. Okay, let's directly jump into the very first detection, the GW150914. This was a remarkable event. My job is to convince you why did it get a Nobel Prize. Like, okay, could be just any other astronomical event, but no. Why? Okay, let me spend just few minutes on this. Of course, Arun must have told you that these people had the notable contributions. Sadly, Rainer Weiss passed away, I guess, a few weeks ago. But this was first of all the very first observation of direct gravitational wave. Basically, it's a direct observation of the gravitational waves. Why? Because, like, of course, you might have heard about this. There was, like, indirect evidence of the gravitational waves inferred from the orbital decay, the orbital period decay from the binary pulsars, which also led to basically a Nobel Prize in 1990, around something like that. It was given to Hulse and Taylor, who discovered it, and that also led to develop interest in the gravitational waves, basically, or modeling the templates, accurate templates of gravitational waves, right? And from there on, all the interests arose basically, and then the LIGO interferometers were designed to directly capture this. So of course, this was, in that sense, it's remarkable that we are directly seeing the gravitational wave, not we are inferring it from some other quantities, like, for example, tracking the orbital period or something like that. But as you can see from here, that the signal that we observed from this event was, of course, seen in the two detectors at that time. These two detectors were operating, the LIGO detector at Hanford H1 and LIGO detector at Livingston. And here, as you can see, basically the two signals that were observed in the two detectors lie on top of each other after accounting for the time delay, which is basically due to because the detectors are placed at different locations, so you have to adjust for the time delay between them, right? If gravitational wave will take longer for to arrive to detectors which are farther in its path, right? So, but if you subtract these signals with, you know, the predictions from general relativity, what we call template, then you see the residual is very much consistent with random Gaussian noise. And so random Gaussian noise is something that you would expect in absence of, you know, gravitational wave signal. Yeah, your data will just, I mean, in the ideal universe, having assumed that you have taken care of their bit complexities in the data. Sometimes it could be non-Gaussian, sometimes non-stationarity, but assuming that if you have taken care of that, then yeah, the remaining part of data should be consistent with Gaussian, as you can see, right? What does it tell you? It tells you that the signal matches. First of all, I forgot to tell you that you can see by eye that there is something, there's some pattern, right? You might have seen from in the Arun's talk, like how gravitational signal look like by eye, but most of the cases they'll be buried into noise, and by eye you will not be able to see it. So this signal was really loud, that you can clearly see. But such signal can also be produced by glitches whatsoever. So you cannot say directly that these are gravitational signal, but okay. So there goes some sophisticated data analysis in proving that they are indeed gravitational signal, not some background triggers. Okay, but okay. So as I was mentioning, now you can clearly see that the signal matches with GR prediction very well. Now you can say, okay, that's fine. What is the big deal in it? Well, as soon as general relativity was formulated, it has always been subjected to various tests. But as I will show you again in, let's say, 2 slides later, testing general relativity to gravitational waves is completely new, basically, regime. And I will try to focus there what I am telling. But let's go on. Okay, maybe I'll just introduce one more thing here. This is nothing but what is called chirp behavior of binary black hole signal. So basically, you take the data chunk that I showed you before, and you do discrete Fourier transformation at a small, time windows, and yeah, then you plot it. Then you see that frequency evolves with the time, and this is just characteristic of binary black hole signals. Okay, I'll be showing lot of time frequency signals because they look good. Okay. Secondly, okay, I showed you that signal matched very well with the GR predictions, and I will tell you in a slide later what it actually means, right? Why it is a big deal that GR actually, predicted it very well. But at the same time, what can you do, as I said, that you know that this part of the data contains a signal, so then there are tools that can enable you basically to obtain its parameter. Basically, what you do is, like, you have data, just try to compare your templates, GR predicted templates, with various parameters, and see which one fits the data best, and that will be roughly your parameters. Basically, there will be some uncertainty associated with it because of the noise, but yeah, like what is your knowledge region of those parameters. And it was found that the masses were like around 36 solar or around 30 solar, so both primary and secondary component. But prior to this detection, okay, the maximum black hole mass that were observed were from low mass X-ray binaries, okay, and the maximum mass was around 20 solar mass, and most of the median of those, the black hole masses from low X binaries was around 5 solar mass, which will again be important in my later part of the talk. But you can see then this 30 solar mass, the question, how do you explain it, right? This is the data, and it is telling you that there are black holes above 20 solar mass. How do you explain it? We'll come back to it. So you see, interesting, right? It is telling you how do you explain this in astrophysics, like how would you form such a heavy black hole. Coming back to the question that I posed slide before, that GR predicted this signal very well, right? What do I mean by that? As soon as GR was formulated, there were various tests that were done to verify its predictions, but all of those tests were basically either in the weak field or quasi-static limit, or in moderate self-gravity limit basically, but slow dynamics. For example, there were tests that Einstein himself did. Okay, he predicted the precession of perihelion of Mercury in 1915. Okay, and also in the 1916, I guess, there was solar eclipse, so you could also compute the bending of basically the light because of the sun, and he actually showed that GR predicted well. But all of those tests were, as you can see, the Newtonian potential, which is related to your the strength of gravitational field, right? If you just compare with the c square dimension, if you make a dimensionless, if it is comparable to c square, which is the relativistic limit, but you can see the Newtonian potential is around 10 to power minus 8, and the corresponding velocity you can compute, right, if their bound system is 10 to power minus 4. So it's like very non-relativistic. So this just tells you that, okay, I mean, it just tells you that GR is good, okay, but in the regime when the strength of gravity is very like kind of weak, and also the time scales involved are very like kind of large, right? But then, as I mentioned about this, the Hull's that I mentioned about this, the detection of the inference of gravitation indirectly. There also it like kind of we probed the gravity, but again you see that even for binary pulsars, that potentials and the corresponding speeds is of the order of 10 to the power minus 3. This is kind of okay, moderate self-gravity, but the dynamics is still slow here because the binary pulsars are very far, really far from each other. But if you go to binary black hole merger that we have seen here, for example, and you can compute that near the merger, you can do Newtonian calculation, that velocity approaches almost about half of the speed. Now, what it is telling you? This is telling you we are actually probing gravity in the strongest possible regime, and still GR is valid. This might, maybe it doesn't strike you, but this is very, and also at the same time, when you are probing binary black hole mergers, the curvature of the space-time is changing at the time, or at the time scales of milliseconds. It's a strongly dynamical also, and still GR is holding tight. It's a remarkable test of general relativity. So now you see why this event basically was given Nobel Prize. Okay, now let's go back to some other interesting event. Okay, I'll just talk about notable events. That doesn't mean that between this event and this event we did not observe other events. We observed it, but I won't be able to talk about all of them given the time constraint. I'm only going to talk about those events which changed that understanding completely that we had before the detection of that event, right? So that's how I'm going to basically talk about. So this event, what is called GW1770, is started an era of what is called multi-messenger gravitational astronomy. Okay, now what happened is that that we saw basically a binary neutron star in spiral, which lasted around 100 seconds in the, as you can see, in the sensitivity bandwidth of the LIGO-Virgo detector, which could be let's say 20 Hz to 500 Hz, and you can clearly see these chirp-like signals in the my figure is cut, but in the LIGO-Hanford and the LIGO-Livingston detector, we do not see this. You cannot see by eye in the Virgo detector, but let me tell you that this signal, the distance was estimated around 40 megaparsec, was well within the horizon distance or the maximum distance out to which these detectors can basically detect. This signal was well within the horizon distance of all of these detectors. So not detecting this signal, basically not seeing these signals in Virgo also is an information that okay, it was within this its sensitivity volume, but we did not detect it. So that helped constrain. So the information from these detectors helped constrain the sky localization, right, of this binary black hole, binary neutron star signal to just a few, tens of degrees square, and the distance was very small. So if the distance is small and the sky area is just like few tens of degrees square, if you compute the sky localization for any general binary black hole, it will be like a few hundred square degree. But because of this, the fact that we saw this event in all of these three detectors, we were lucky enough that this came from very short distance. We were able to localize it to very small sky localization, sky area, and since the luminosity distance small, we could actually pinpoint. So there would be just few galaxies, right? Because the distance small and the patch is small. And soon after, basically, yes, this GW was detected. The astronomers were informed that we have seen basically a gravitational signal, and this is this patch of the sky where it came from. And then basically astronomers follow it up if they to find if there is any electromagnetic counterpart. And what happened is that since neutron stars have matters, right, when they merge, there are lots of, I'll discuss those things, try to discuss those things. If matter is involved in such violent collisions, there will be lot of physical processes that will be producing EM basically radiation, and it turns out that this system emits electromagnetic waves in all of the spectrum. Let's go one by one in few minutes. So what happens soon after the binary black hole, basically the gravitational signal was detected, around 1.7 seconds after, a short gamma ray burst was also detected by Fermi gamma ray burst monitor and integral. So as you can see here also, like this is the LIGO Virgo the basically localization, and this is the sky patch that Fermi GBM can basically look, and it was confirmed that it came from the same localization. This proved that BNS mergers are basically linked to short gamma ray bursts. Prior to this detection, this was just an hypothesis basically. It was just a hypothesis. What do I mean by gamma ray burst? I mean, I cannot go into details, but there is some cartoon here basically. So when you have binary black hole, binary neutron stars, when they merge basically, there are a lot of matter, so there is some remnant. Let's say you don't know about the remnant, but there will be a disk of materials, right, confined within some radius, and there is details from magnetohydrodynamics, etc. That I mean we can go into details after the talk. That launches a jet. Okay, as you can see here, this jet, and this jet basically you can do simple thermodynamic calculation to show that it will be basically in the gamma rays spectrum. You can just, it's not difficult to compute it. So, and here basically what I am showing you is this, like this chirp signal, and this is the peak time where the gravitational wave amplitude peaks, and 1.7 second, almost around that time you see the peak in the photon counts, right, as you can see from the from in the Fermi GBM and integral detectors. Now there were, as I mentioned, so the EM radiation was basically seen in all of the spectrum. I cannot go through it, like in a gamma ray, as I mentioned, gamma ray burst, there was X-ray, the jet, the interaction of jet with the medium produces X-ray, and then there was UV. I just would like to focus on basically the optical part of the radiation and infrared, because there interesting in the sense that I'm just highlighting this part because there is some process called R process, or the rapid neutron capture. So you know, right, the neutron star, name itself neutron, where does it come from? It means it is made of lot of neutrons, right? So when they merge in the disk, basically you have lots of neutrons. The concentration of neutron is high. So basically what happens, things like, you know, heavy metals, you might have heard that supernovae, you know, process, etc., are responsible for making heavier elements in the periodic table, right? Because, you know, they start from hydrogen and then go to helium and then carbon, oxygen, blah blah blah, and up to the iron, because iron is the most stable nuclei. So but they cannot form elements higher than iron, right, in basically the way supernova physics work. But here the iron can capture lots of, basically in the disk there will be even some amount of iron present, and then they can rapidly capture neutrons, and they can form lanthanides. Lanthanide is defined as some elements with atomic number greater than 57 or something. So by that I mean just heavier elements like gold and platinum. This now, so basically this tells you now that the BNS merger basically produces those heavy elements that basically may have, not may, we have this gold and platinum, and this is one way now we understand how heavy. So you see how remarkable, right, these detections were. I mean, at least to me, these were very interesting. Now, okay, what else? Like, okay, this was, what else? Like, can you do with GW17 or 870? There are a lot of things that you can do, and it's not just thing we can do. This actually changed our understanding by a lot. For example, the speed of the constraint on the speed of gravitational waves. Okay, GR tells you that its hypothesis is that basically that the speed of gravitational waves should be the same, or yes, same as the speed of electromagnetic waves. But then, as I mentioned, like, it is always subjected to test, right? And what could be better test than this? The fact that we know that we saw gamma rays and gravitational signals from the same system, and they traveled across 130 million light years, and still the differential arrival times were just 1.7 seconds. You see, that places a bounds on the, you know, the difference between the speeds of the two waves, the gravity waves and the electromagnetic waves, and the fractional difference is just 1 part in 10 to the minus 50. This is essentially saying that gravitational waves travel at the same speed as the electromagnetic waves, right? And this ruled out, just this fact ruled out many modified gravity theory which were proposed to tackle dark energy or cosmological constant. That was that Sri Ram, I guess, did not mention much, but yeah, that appears as one of the problem where they took liberty to change the speed of gravitational wave, okay, to answer some of the problem related to dark energy model. You see, right? Now this forced them to change their ansatz. One of the founding principle of special relativity, and for that matter general relativity, is Lorentz invariance. And the Lorentz invariance basically tells you that the energy is related for any, let's say, massless particle. Maybe it's a photon, a neutron, whatever particles that have massless, it should be just E equals to Pc, all right, or E is equal to Pc square. But there are also modified theories of gravity which break this Lorentz invariance, and in those theories, basically, you can take the liberty to change the dispersion relation, and the fact that we saw around like 3,000 cycles, as I mentioned, right? Arun might have mentioned for BNSS, because the total mass is very small, so the duration for which we observe signal is huge, and you can compute the number of cycles. If you increase the number of cycles, basically the thing that we measure in gravitational wave is phase. So any small deformation basically accumulates. So if you detect higher and higher cycles of gravitational wave, it becomes much more precise to probe basically the corresponding physics. And this system, this event basically put a bound and saying that there was no frequency dependent propagation. Gravitational waves are non-dispersive and consistent with GR. Similarly, you can also test another foundational principle of the general relativity, which is equivalence principle. Rather, here I will show you the test for the weak version of it, which just tells us that all the basically particles, or let's say in this case massless particles, will travel or follow the same geodesics, right, irrespective of that, of its nature. Now the fact that we saw both gamma ray, again I am coming back to the same thing, the fact that we saw gamma ray and gravitational wave from the same system traveling through the same path, so they would face basically the same okay, this is also related to something called lensing, but okay, we will not go through it, but the idea is this, very simple idea is that a source is here, earth is here, a gravitational wave or gamma wave, basically gamma rays is coming to you, it will face intermediate objects in this regime, right? So let's consider all those, replace all those intermediate objects by some potential, okay, described by U of R, okay, and this will produce a curvature. This is a standard prediction of general relativity. It will produce a bending basically, and that will cause Shapiro time delay, right? If there was no intermediate object like galaxies or other international medium whatsoever, everything described by some potential, then delta t or Shapiro time delay will be 0. And you can very easily compute it. It will, of course, as I say, it will be linearly proportional to the your integrated potential, and it is basically proportional to some quantities called gamma basically here, and it can show that the difference that the two waves like gravitational wave and the gamma ray face basically in this Shapiro time delay is of the order of 10 to the minus 9. Again, it is telling you that they follow the same geodesics, which means that the equivalence principle is valid. And this, the bound that I am showing you is many orders of magnitude stronger than any other test that existed before. You can do the same thing with these neutrinos, right? Supernova neutrinos. So you see how our knowledge got refined, by so much. Similarly, this also provided strong field test of gravity. Again, as I mentioned you, we saw almost 3000 cycles in the band, and we track, as I mentioned, we measure the phase, right? So any small deviations in the predictions of general relativity in terms of its phase will accumulate over 3000 cycles, and you will be able to, if there is, let's say, even if a small deviations, let's say 1 radian at the end of 3000 cycles in the phase, you will be able to detect it, or you are basically you will be able to measure it, because it will create sufficient mismatch between your template and signal. So what we do basically is like, you can directly probe the GR predictions for this in spiral that we have seen. GR predictions for the phase that we measure directly is given by some theory called post-Newtonian theory. The details are not required here. It has in some form which is expand, like phase as a function of frequency can be given order by order in terms of frequencies, okay, in the frequency of the gravitational wave, and you can basically try to measure each Pn coefficients that basically lead to this phase, and each Pn coefficients is basically uniquely determined by general relativity, right, given the parameters of the binary system. And then you can ask that, okay, what if I modify each Pn coefficients, right, and see, for example, like this, you just introduce some deviation, and then you can ask whether these deviations is 0 or not. If deviations are 0, that means basically the phase that we are measuring is consistent with GR prediction. If there is some evidence for non-zero deviation, that might force you to think that there could be something, some other hints of new physics or something like that. That basically it will trigger you to think more, right? And what we saw is that these deviation parameters basically, as here is what we call the measurement uncertainty or the posterior that you can measure from the data. So what you do is, like, you have GR waveforms, you introduce some corrections, and question is, can we put bounds on those corrections basically, or deviations? And we see that those deviations are, for example, this is 0, 0 line, right? All of the posterior contains those 0, 0 lines, which is like, that means that your basically the phase that you have measured is consistent with the GR prediction. There is one parameter that I would like to discuss is like -1p and so on. This does not appear in GR calculation. This is related to what is called dipole radiation. Okay, this does not occur in GR because this will require breaking of the mass conservation, which right, in general relativity the total mass is conserved. But there are theories, okay, gravity, where dipole basically this conservation is broken, and that leads to dipole radiation. So you can fictitiously introduce -1p corrections in your GR phase and try to bound that parameter, and see what happens. And it turns out that you can see that the dipole radiation is consistent with 0. This is the dipole radiation part, right? And it's consistent with 0. It's saying that no, GR is again, like this event is telling you the GR is consistent, the data is consistent with GR prediction up to the order of 10 to the power -5, you see. And this bound is much again better than any other astrophysical probes. Let's see how many tests we are trying to do, and every test basically is confirming that, well, and again in the later talks also we will keep refining these bounds much better and better, and at the end, if you really want to go about formulating some other theories, gravity, you really need to sit and think a lot, because this data simply will either consent you or reject your hypothesis. Okay, so now another thing that this particular, see how much time I'm spending on this event. Another thing this event basically allowed us to do is to understand the internal structure of the neutron star itself. What do I mean by that? Okay, so these are basically the spiral neutron stars, right? These are matter, not like black holes. They are kind of point particles in vacuum, right? In general relativity or in the space-time basically. But if you have matters like neutron stars orbiting each other, the companion or the other neutron star will basically tightly deform the other, the other one. So one will deform the other one, and like vice versa. And this deformation, how much it will get tightly deformed, it will depend on the intrinsic details of the neutron star system. And the intrinsic detail is basically contained in what we call equation state. And that equation state is nothing but that relates your pressure to the density and temperature. So all the microphysics basically, like for example, there are various in the neutron star. If you try to model it, the outer crust look like basically a kind of a crystal basically, and then if you go deeper and deeper, density increases and the temperature could also increase, and basically there are other physics, very complicated physics can occur. For example, super fluidity can come in. There are various the microphysics, but all of these will affect your equation state, and that equation state basically will tell you how much tidal deformation will happen basically. So, and the tidal deformation is contained basically, if you do a calculation, even at this Newtonian calculation, you don't need to invoke the complicated GR predictions. You can show that you can capture the tidal deformation using a parameter called tidal deformability, which is inversely proportional to what is called compactness, which is like m by r. So it's inversely proportional to it. So more compact it is, basically it will be harder to deform it, right? So, and this proportionality constant is what is called love number. Again, given equation state, you can compute basically these numbers, kappa 2, and if you know the mass, you can compute radius. So, but the thing is that this tidal deformation, right, this tidal deformation created by other objects basically induces a quadrupole moment, and if you know about the basic GR, any quadrupole moment, the double time derivative basically produces gravitational waves. So this tidal deformation is directly basically measurable from the phase. You can compute, you can measure this tidal deformability from the basically gravitational wave form. Right? So each neutron star basically has its own tidal deformability, but at the level of waveform, we can only measure some certain combination of individual basically this tidal deformability. Okay, details are not important here, but based on our measurement of tidal deformability, okay, these are the predictions of basically the tidal deformability from different equational states, and you see that this is the range of the tidal deformability allowed by the data. So all these equation states are ruled out, and it tells you that so the tidal deformability measurement tells us that if you know the tidal deformability, you can basically constrain your equation state, and based on that you can just for a given mass you can compute your radius also. For let's say you are interested in 1.4 solar mass, then you can compute your radius, and you can show that it is around 11 to 13 kilometer. Now this tells you that extremely soft equation state and both extremely soft equation state and extremely steep equation states are not allowed, because if you have extremely soft equation states, this would predict very small radii, because for such equation states pressure rises very steeply with density, so it will be very difficult to form high radius, as you can see, right? So now of course like this result is just like, okay, I'm just telling you this just method, one way to understand about the internal structure of this thing, but just based on one event it's not possible to exactly go into the details of intrinsic properties or microphysics. But let's say in future if you detect many more, let's say few more binary neutron stars, then this method will become has the potential to basically unravel the mysteries of the intrinsic physics that basically occurs inside the neutron star. And neutron star, as you know, it's very exciting state. It has density comparable to nuclear, even much it is more concentrated than even the nuclear density. So their range of physics, okay, goes into modeling it. And I'm just telling you, this neutron star binaries is one of the probes that you can use to understand about those physics. Okay, now other thing that this event also allowed us to measure what we call the local expansion rate of the universe. I think Sriram mentioned it, but he did not name it. Maybe it's called Hubble's law, and what Hubble's law is telling you that if the farther galaxies reaches faster, basically, right? If you would have done a basic cosmology course, it tells you that the recessional velocity is proportional to the distance in the local universe, and the proportionality constant is what is called Hubble constant, and this Hubble constant is basically just like appears everywhere in cosmology. You require basically S0 for more dark energy matter everywhere, curvature of the whole universe, space-time of the universe. So it's a fundamental parameter in the modern cosmology. Now the velocity, of course, is just related to the redshift. Redshift, you know, I guess, is like, okay, let's say if you have a system, let's say galaxy, etc., and it's moving, away from you, and if you observe some spectrum, you know that if it was not moving with respect to, that, you see some shifts in the spectrum line, right? And how much it has shifted, you can infer the redshift from there. And you know from Doppler shift in the local universe is just basically velocity. Now you see, again, for this system, we observe gravitational wave signal and electromagnetic signals both, right? And I guess if you would have attended Arun's talk, you know that from gravitational signal, because we measure amplitude and phase, right? And from amplitude, we can directly infer what is called distance or the luminosity distance, if you really care about the precise name. But the EM spectrum, for example, the kilonova, etc., very quickly pinpointed the host galaxy, which was NGC, as I mentioned in the very first introduction of this slide about this event, that we just had a few galaxies, right? And it was very easy to pinpoint which galaxy this kilonova came from, and the redshift was inferred to be this. Once you know the redshift, you know the recession velocity, and you know the distance basically from gravitational signal. So you have on one hand the luminosity distance, on the other hand you have redshift. So, and these two are related with your cosmological models. You can have cold dark model, warm dark models, or lambda c. I mean, there are various models for describing the dynamics of cosmology or the universe basically. And so basically then you can basically so now, using, as I mentioned, you know the DL and redshift, and then you can basically directly constrain under certain cosmology. Here we assume, let's say, lambda CDM, the standard model for the universe. If you assume that cosmology, then we find that H naught is considered to be this. If you want exact figure, it's basically in this figure, the x-axis is H naught and y-axis is the posterior distribution. And you see here the standard tension that you might have heard between the local supernova physics result and the CMB result. Okay, this is the tension. They do not agree. But unfortunately or fortunately, the gravitational wave information lies exactly in between them. It's just telling you that basically right now, based on just one event, the posterior is not very constrained right now. But let's say in future, if you see, I'll tell you, if you observe, let's say 4 or 5 binary neutron stars in the future, in the third, even with the O5, okay, observations, O5 detector sensitive, etc., we'll be able to probe this H naught, the fractional, within 1%. That will either confirm or resolve the Hubble tension. How exciting this field is. Now let's switch to some other event. I guess we spent too much time, but it was worth it, right? This event, and I hope we get to see more of them. We were lucky enough for this event, the last event that it is, because it was from very, close by universe, and the SNR were nice, so you could infer. The sky localization was small enough, blah blah. Anyway, let's switch the gears to other event, other notable event, which occurred on this 12 April 2019, around, I guess, the first part of the third observing run. Okay, so this event, for example, it showed that the two masses that we measured for this event was very different from one. Now you might say, oh, what's the big deal? Well, all of the astrophysical understanding that we had before detecting this event was that it's very hard to form binary black hole systems whose masses differ or basically are not very similar. So question is, how would you explain it? Like, there are various channels, this is called standard isolated field binaries, where two stars evolve, in isolation basically. They're very far apart. They go through this usual supernovae. Their details, for example, that of course I cannot go into, I have time constraint, I want to show other things, but there are various formation channels for okay, let me spend just 1 minute. Okay, so basically you can have two stars evolving in isolation. They can come closer. They evolve in, like, about how stars evolve, right? During they go from the normal, what we call I think I messed up. Yeah, what we call basically the main sequence, and basically where it is hydrogen burning, and then it goes to red giant, and then basically size increases a lot, and then it forms basically a common envelope phase. The common envelope phase is very complicated to model, but some magic happens, and then because of the dynamical friction, etc., these binaries come very close, and then they can go through supernova individually. They can form binary black hole. We can discuss the details of the physics offline, but this is how people thought that binary black holes will be forming. Other cases is like you can have a star clusters, like global clusters, where already, you have many black holes that have formed through, let's say, this, and then they are dynamical in nature because there are small clusters, and then things can be flying by, for example, so randomly they can basically form a binary, and then those binary will be seeing it. But all of these basically channels, it turns out, if you do the physics detailed modeling, they predict that mass ratio would be very close to 1. Okay, but this system again changed our understanding. It says that, and the system means what? This is data, and data is data. Either you may be wrong in your theoretical modeling. Okay, but so then still I think I'm not sure this question is resolved, but of course it challenged our usual understanding or the simple population models. But we can discuss about the possible resolution later offline, because it's a active field of research. And this particular event also, it's also important for fundamental physics, for example, because if you go and do GR, if you do and try to compute the waveform using GR or in certain approximation, what is called post-Newtonian theory approximation, it turns out that if the mass ratio is different from 1, there are harmonic structures of gravitational wave. For example, so gravitational wave does not have just one fundamental frequency. You can have an array of the series of frequencies that it can be composed of, for example, and it turns out that if the mass ratio is very different from 1, these higher harmonics get excited, and this event basically, since mass ratio was not 1, this allowed detection of those subdominant harmonics or the higher harmonics, whose frequencies are higher than the dominant frequency. For example, a particular gravitational signal for such a system, let's say mass ratio is not equal to 1 at all, and there is also something called inclination angle, okay, which is related to how orbit is inclined with respect to the observer. Then you see that there is beating pattern, right? This is the total signal that you see, for example, one of the polarization Arun might have told you, and you see the beating patterns, right? And if you remove from it that basically this dominant frequency, which is very smooth, then the residual basically is just like higher harmonics. So any beating pattern, or for that matter, is basically an additional information. Any additional information is always useful. So this additional information, for example, higher measurement of higher harmonics, allows, for example, breaking the degeneracy between distance and inclination, and hence improving your measurements, and hence your Hubble parameter estimation. So for that matter, NSBH kind of systems, where neutron star mass, it cannot exceed more than 2 solar mass, and black hole can be anything, so mass is larger, right? So those kind of systems we are eagerly waiting for. because higher harmonics will be visible, and then there will be breaking the degeneration, and measurement of the distances will be much better, and the Hubble parameter estimation. So even if you do not have binary black holes, binary neutron star is fine, but if you can see those NSBHs in abundance, then also we can measure Hubble parameter with sub% accuracy. Nice, no? But there is other things also. Like if you observe higher harmonics, it can allow you to do another test of general relativity, because if single harmonics is enough to give you all the parameters roughly, but kind of the no-hair theorem for each black hole, right, that they are very simple in nature. They are described as just mass and angular momentum. So similarly, we would expect the binary black holes, for example, would be just explained by the individual mass and mass and spin of the individual black holes, right? So you can infer that from the dominant harmonics and test that with the other harmonics and see the consistency. If they are consistent, again it's telling you that it's basically, again this is independent verification of general relativity in the very strongest regime, right, as in the merger part. So see, you can come up with various states of the general relativity. Question is about its power. What is the power of your test? So we keep on coming with such basically tests just to prove that no, Einstein was right. Okay, now let's change gears. Again, after a few months, I guess on 21st May 2019 during 3rd of January, we saw another event. It's called GW190521, and this event, the primary mass that we inferred was in certain regime. I'm sorry, I'm just giving you information, but this is the aim of my talk. I'm just information, but this is the aim of my talk. You see, all the detection, how they change our prior understanding. And all of these questions, believe me, still are active research area, okay? We do not have much, none of these questions that I am telling you, unless otherwise I will state it, they are basically still unresolved. So you saw, so basically when you do this, the standard theory of like massive star evolution. So let's say if you start with, let's say 20 solar mass, 0 age main sequence star, okay, the initial mass of the star, and if you evolve, like as I mentioned before, okay, like hydrogen, helium, blah blah, etc., and then they go through supernovae. You might have heard this usual story, and then they form black holes, right? But it turns out that if you start with really high mass of the initial star, let's say 120 solar mass, initial mass of the star, not the black hole, okay, it turns out it has core temperature of around 10 to the power 9 Kelvin, and that temperature and the corresponding density, photon starts disintegrating into electron positive pair. Now if you know, I guess you might have heard about the hydrostatic equilibrium that exists in the stars. Stars are stable, right? Why? Because these photons, right, gives you the radiation pressure that balances against the gravity pressure, right? But if you start removing, okay, photons at the cost of forming electron positive pair, basically you are starting in instability, you are softening the equation state, right? That instability can completely destroy the star and no remnant will be formed whatsoever. This is one of the predictions from theoreticians who models the evolution of massive star. And so in the standard theory, there was a consensus that there will be no black hole in this regime around 60 to 120 solar mass. Above 120 solar mass, these black holes can be observed by the nucleus, and then again it becomes stabilized. So those black holes can form. Okay, but you see the primary mass that we saw of this event was exactly in this gap that was predicted by the theory. Well, the theory was in very idealized version, in the single isolated star, not even binary, blah blah, there is very complicated physics. So this forced those theoreticians to revise their calculation. Okay, now there are a lot more studies and new understanding, but at that time when we detected it, when LVK collaboration detected it, basically it was thought that maybe these first generation stars, when they found they died, they found black hole in the usual sense below 30 solar mass or something, they might have formed a binary black hole systems merged that we did not see. We do not have a detector at that time, but we are seeing the remnant of those second generation binary black hole forming binary. So remnant from one binary black hole, remnant from other binary, they can form binary. Those are called hierarchical mergers. But this could be as well something else, primordial black holes. Still the questions I don't think are settled now. And the final remnant black hole was estimated around 140 solar mass. And this is kind of a regime where it falls in the regime of parameterization, which is called intermediate mass black hole. And this was also direct evidence for intermediate black hole. As far as I know, there is no any other electromagnetic probe, direct electromagnetic probe for existence of intermediate mass black hole. These are very important objects if you really want to understand the evolution of, let's say, supermassive black hole, which resides in, I guess, all of the galaxies, in the centers of all of the galaxies. So you see, I hope you are able to see the importance of detecting these events and how they are forcing us to rethink about the astrophysics. So it's not about just fundamental physics that we're going to do. It's, actually, it's really providing you a new window to think about the universe. Let's now go back to some other events. Let's say, so, okay, I've ordered the events by the date of their occurrence, okay. So this event occurred after whatever I discussed, just to, let you know. So then this event occurred, which is called GW19 at 14. Now in this case, the secondary object, the secondary component mass lied in a regime which was again kind of not expected. It falls in what is called lower mass gap. And this is basically a kind of empirical mass gap, I would say. It says that, again I mentioned, right, the black hole masses that were inferred prior to detection of gravitational systems, binary systems, they were inferred from low mass X-ray binaries. And most of the masses are basically, it clustered around 5 solar mass. There was no black holes below 4.5 solar mass or something. And you can do theoretical calculation, etc. for neutron stars, depending on equation of state. People found that you cannot exceed more than 2.2 solar mass something. After that it will become unstable and it will collapse to black hole. So there was a kind of a gap between 2.5 roughly 5 solar mass, where it was thought that no comparative object would exist. But you see, this event is telling you the secondary mass within its measurement uncertainty, it lies in that gap. The question is, what is it? Is it heaviest neutron star or lightest black hole? Any implication will have its own, any inference will have its own implications. For neutron star, this will ask you to revise your understanding of equation state, or how basically these neutron star collapse into black hole, etc. You understand how important these discoveries were. Now, another event, for example, the very latest event, this has primary in this mass gap. So it's not just this event is alone, there were more events. Okay, I think I'm ending towards basically, I do not have infinite amount of time. So I will just describe one more single event thing, which is GW25. So this is very recent, you see. This occurred on 14th January 2025. And I just, okay, some of the events that I have discussed here also present in the poster. So you are welcome to basically visit the posters also. I guess this event also is in the poster. So, but okay, just for the sake of completeness, I can tell you that this event that was detected is basically replica of the very first event that detected exactly 10 years ago. But it appears as a very, very loud event, basically, okay, of the self. So it's like SNR is, or the loudness is around 80, which is almost 3 times the SNR of the very first event, and the parameters are very similar. So it's just, kind of, and you can by eye, there's nothing is done. It's just like some bandpass filter to remove the noise, I mean the nonsense part of the data. Otherwise there is nothing else being done here. It's just by eye you can see, very nice. You see, and the time frequency diagram also you can clearly see. And this event, of course, as I said, right, that it has very high SNR. It allowed us to refine our understanding of the bounds, for example, for the in-spiral test, right? Because as I mentioned before, right, you can probe like post-Newtonian structure, or basically the coefficients that appear in the phase evolution, and that coefficients are uniquely predicted from general relativity, and you can put bounds on each of the coefficients, right? And you can see this event single-handedly, because outperformed all of the events combined before its occurrence, which is like GWTC4. I will come back to this definition. This was after GWTC4 was released. Okay, so this event is not part of GWTC4. Okay, so you see the GWTC4 combined result rate part, and you see the bounce is much smaller just based on this event. This is because of the fact that it has very high SNR. Of course, this -1 pn thing, it just proves very early in spiral, so it cannot win against the GW17 or 17 because we had seen so many cycles in the band. Okay, and it really probes the early evolution, but for this system we do not see the early in spiral part, only late in spiral part, so we cannot probe the dipole radiation much better. But you see all the higher PN coefficients which basically probe the higher frequencies are much better just based on this is the bounds, right? And also I am sorry, given the time constraints I cannot go through it, but the fact that we saw the the late in spiral, or the basically the merger ring down part, what is called ring down, I guess you might have heard in Arun's talk, that when two binary black holes form, they form a deformed Kerr black hole, and then they settle into a stable Kerr black hole by emitting gravitational wave in the set of quasi-normal modes. And quasi-normal modes, if you can observe them confidently, they will be kind of so short gun of the or a smoking gun of the existence of black holes. I mean, we can discuss the details later. So basically that tests what is called no-hair theorem, and as I mentioned before, the no-hair theorem is that black holes are simples. In GR, black holes are very simple. They are just describing mass and angular momentum, and they dictate this the quasi-normal modes. And if you can see many modes which happened actually in this case, because the SNR was huge, so we were able to see more than one mode in the ring down, and that allowed to verify the no-hair theorem. It also allowed what is called Hawking's area theorem very well, where basically it just tells you that the final area of the black hole, okay, is greater than the sum of the individual black hole area. But you can look at this thing, and we can discuss offline also, because I have other things to discuss. I guess I have just 5 more slides. Okay. Okay, so I'm done with the individual events discussion, but there are many more other events that I did not discuss. You would say, why? I mean, of course, it's a $1 billion project, and you have discovered, events, and you're just throwing out information just like that. I mean, it doesn't make sense, right? So now let's see what happens if we include. Okay, individual events analysis is good, it's fine, but it has its own limitations, and I don't think I'll be able to tell you the details why just looking at the individual events can mislead you. So it turns out that you should actually look at the population of all of the events, how they behave, okay, because they inform everything. For example, the prior that we use for the Bayesian analysis to measure the parameters, they will get affected. So it's always ideal to look at the population of all the binary black holes that we have seen. Here, as I mentioned, I will tell you the definition of GWTC4 catalog. This catalog, there is a catalog of the events which basically encode all the detection until 4th observing run. Okay, I guess until January 2024. Okay, so there was like the first detector happened in the first observing run. Okay, of course, by definition. Then O1 O2 basically, yeah, the second observation run was also done, and then if you combine O1 and O2, the observation run 1 and observation run 2. If you do not, by the way, if you do not understand what do I mean by observation, it's just that the time when these detectors were on, sometimes they are off because they are taken care of, well, for example, to enhance the sensitivity, okay, blah blah, right? So when they are on, we call that they are observing. So that's why that is called observational run basically. So during those observational run, O1 and O2, we had like A1 detection, and the first part of O3 basically we had 44. You can see here, and we LIGO Virgo collaborations have basically released all the data until the first part of fourth observational runs, and for like it will be followed up by the second part, third part, blah blah. The detectors are still running, and the total detection as of now is around 218 events. And by detection I mean like any event which has, you can compute for each event some probability which is called astrophysical probability. If it is greater than half, we call that as event. Okay, this is the defining criteria for a particular trigger that occur in this detector as an event, right? If it's astrophysical probability less than half, it's just a noise trigger basically. And this is the time frequency diagram I follow the thing. Right? Question is, okay, what does the population say, right? This is the question we are interested in. Are most binary black holes around 30 solar mass? Or do we see evidence for mass gap? Do black holes typically have low spin or high aligned spin? What is the centricity distribution of the, sorry for the typo, the binary black hole orbits? The cosmic merger rate density. This distribution can probe models. So why are we interested in this? As I showed you, right, there are different formation channels, like can be like isolated field binaries or things happening in the star cluster, or could be primordial origins, etc. They will predict a population of binary black holes with different mass, different spins, different centricity, something else, okay, that we can different merger total in, let's say, in particular volume of the universe, they will produce different merger rate, yeah, total merger rate. Okay, so if you, and on the other side we have object distribution of this events, the parameters, and you have object distribution. The question is, how do you map this object distribution to the astrophysical or cosmological, whatever your favorite model could be? This is the question, right? Only then you will be able to probe the physics, astrophysics. For example, how particular parameter during the common envelope phase distribution changes the spin distribution, okay, of the binary black hole population that results during the isolated field binary evolution, for example. So then that way you will be able to probe basically the physics during the common envelope phase. Similarly, you can basically probe the cluster dynamics, or it could be the neighborhood of the basically supermassive black holes near the nuclear clusters. So you see, right, the power of the population analysis, why we are trying to do it, is the population where all the information is, right? You have to do this population analysis for all of them. Even for the test of GR, you have to combine the information from all of the events. You cannot throw the information that could be lying, right, from other events. So population analysis is not just astrophysical, it's also for fundamental physics. You stack all the results properly, coherently. You get all the information that you can basically, extract all the information that you can do from the data, right? For example, this is the object distribution. This is the object distribution of the primary mass and secondary mass. These colored points are from like O4 and 128 new detections, and the gray are basically from the previous runs. And you can see from all these points, these lines are basically the constant mass ratio thing, and this is like these points around very equal masses. When the two masses are very equal, this line, so any binary which is near to this is like they have very equal masses, and you see the most of detection actually have the mass ratio which is very near to 1. You see, there are only few which depart from this train. Now this is a difficult job to answer which formation channel or channels could have produced them. How would you understand this observation, this object distribution? Well, the question is, on one hand we have the object distribution, on the other hand there could be millions of models. But at the first, if you ask me, I would go with simple astrophysical models, right? Because if you have more parameters in your model than the object data itself, then it doesn't make sense. So you can be doing, you could be just overfitting the. So generally, what in the community, what they do is like they try to fit the this object distribution with a simplest possible model that can capture the features of the data. Basically, for example, you can try to model the primary mass distribution, the distribution of the primary mass that you saw using some mixture model. Let's say some power law in M1 power alpha. Let's say that your one hypothesis could be just power law, that all those binary, or let's say you can say that those isolated field binary that I was showing you, that would produce the primary mass of the binary black hole that LIGO is seeing is following M1 to the power minus alpha, where alpha is some positive fractional number. Okay, it could be 2.3 or whatsoever. It turns out that, as I will mention later, this is not sufficient enough to explain the object distribution, and turns out that there are additional features. Okay, we learn from the fact that we see that when we assume this model, we get higher evidence for this model than just assuming this or this. So let's assume, actually this is a process in loop. You first apply some simplest model, and then you learn, and then you try with other models and compare their something called Bayesian evidences. Whichever has more evidences, you try to basically incorporate that and refine your basically population inference basically. If you do not understand all of this, it's fine. All I am just trying to say, you can come up with your favorite model for M1 and mass ratio and all the other parameters that you are interested in. I am not interested in all those like kind of inclination angle or sky localization. Okay, those are not basically, you assume they will be isotropically distributed, because I guess I don't think binary distinguish between this direction and this direction. I guess, in the sky they can form anywhere, right? But that is not the case with the intrinsic parameter. Okay. So then you can have a favorite models describe a certain parameters, and then idea would be to find out these parameters. Okay, these parameters that describe the parameters of your binaries. These are the parameters of the binary that you are seeing, right? These are parameters of the binaries that we are seeing, and these parameters have the distribution described as some additional parameters which are called hyperparameters. Okay, and then we learn about these hyperparameters from the object data. This is the result. If you do not understand what I said before, just forget about it. Let's just focus on this. Okay, so on x-axis we have like primary mass. On y-axis is like their corresponding occurrence. So basically, it just tells you that what's the probability of having this particular mass beams. It's just telling you the y-axis basically. If you do not understand it, it's called differential merger rate. Okay, it just tells you that in particular beam, how this particular beam is like basically what is its probability. Okay, in the nature basically, or what's the probability of forming, let's say, 40 solar mass primary black hole. Now those data, okay, under certain prior model, when you try to fit it, accounting for the selection bias of the detectors, sometimes like can not sometimes, they always have selection bias, right? Higher masses have higher amplitude, they are easier to detect, but lower masses are not, basically detectable. But this fact you have to undo when you try to do population analysis. Otherwise your population analysis will be biased, right? You'll be say, oh well, I know that object distributions will have higher masses because they have higher amplitude, that will be detectable, but that does not mean the nature is not producing the smaller masses. So you have to account or undo this selection function. There is some tools that has been used to produce this plot, takes account of that. So after taking account of that, this is the result. This is the primary mass that we think, this is the astrophysical, the prediction of the primary mass from the observed data. So you have observed data, based on that we want to predict what would be the astrophysical model that would be producing it, and we find that there are multiple peaks or the over densities in the primary mass. For example, he is saying that there are black holes at 10 solar mass and 30 solar mass which are more probable than, for example, black holes at, let's say, 25 solar mass. How do you explain it? He is saying that in nature the data is telling you, well, the data is data, again I am telling you, is telling you that there are black holes with masses 10 solar mass, 30 solar mass, which are more abundant than in other mass beings. How do you explain it? Again, it's active research going on, and you can contribute. You can get a lot of fame because it's really important questions, and it can help theoreticians or astrophysical modeler a lot. But there is some understanding right now that people think that this 35 solar mass could be because of the pair instability gap. You know, it's not clearly understood that, okay, there may be some clustering happening at the edge just before the pair instability gap occurs, and this one 10 solar mass could be, you know about this, but I mean, this is well consistent with the stellar mass black holes, basically, like that you observe from low X-ray mass binaries. But the GWTC4 result, for example, if you do not understand these curves, no problem, forget about it. You can focus on, let's say, a B-spline model, which is more flexible model, which tries to capture the subtle features of the data, and that also now is pointing towards some local over density around 20 solar mass. A new problem is now added to be explained. It's saying that data is trying to say that there is, but it will of course require more investigations. But again, with respect to the GWTC3, I mean this catalog was until the third observing run, and fourth observing run added more observational data, and now that is telling you with respect to the previous data there is kind of bit more probability for 20 solar mass. Is saying that there is peak at around that. Now we have to explain this, that how like what are the astrophysical channels or whatsoever, it could be cosmological also, that could be producing this 20 solar mass thing. So, and also as I mentioned in the very beginning that there should not be like black holes, right, above 60 solar mass. If that was the case, you would expect like exponential fall up. If there was no black hole above 60 solar mass or something, but you do not see here. So our data is telling you that, sorry, I don't think there is something called pair instability gap, but that could be misleading because this part of the parameter space could be filled up by other formation channels, and you do not know from the data that why should we expect it from first generation black holes like isolated field binary. It could be that hierarchical mergers could be well enough in their their number that is basically filling up this thing. So it's more information is required. Just based on mass you cannot say, like you have to add information from spin. If possible in future, right now we are not able to detect eccentricity, but in future if we can observe eccentricity, then it will help us kind of it will shed more light on this, whether really pair instability gap exists or not. There are some papers, recent papers on this, but yeah, I do not have time to go through it, which claims that no pair instability gap basically exists. Anyway, Similarly, you can basically learn about the mass ratio. As I was mentioning that most of the other black holes lie around mass ratio, right, 1, but few of them were basically scattered here and there. But so as you can see from here basically that the recent GWTC4 result has slightly more probability or more support for models with asymmetric binaries, right, not just near mass equal mass binaries. This is because there were sufficient enough there was good number of candidates which had mass ratio you know, or the posterior extending beyond or sorry posterior support for lower mass ratio. So all of this basically, now this is the data, kind of data driven result. Now it is now completely on to theoreticians or the astrophysical modelers to answer these questions. How do you answer this? And during that process, you basically you understand your system when you try to produce this data, right? And I'm a data person kind of. I'm telling you that this is the result. Now can you answer? Can you tell me which astrophysical models would produce this? And this is really unsolved, and it's kind of mystery right now. Similarly, you can also learn about how merger rates evolves with the redshift, right? And it turns out that currently all the results or the binary black hole merger rate that we see basically evolves with redshift, which is consistent with the cosmic star formation rate. So there are predictions from like theoreticians, like how, let's say at a particular conforming volume, okay, at redshift, what would be the number of the star formation, right, per unit time. So from stars only black hole forms, right? But then if you have binary stars, there is some delay time also to form binary black holes. So you would expect slight deviations from star formation rate track, but still it's within the uncertainty. Right now uncertainty is huge, although the uncertainty you see become smaller with the GWTC4 data compared to the previous result, which was this, you see, and this is because you are adding more events, right? So see how important it is to add more and more events, and in the future we will be able to track it precisely. You will be able to map the whole universe from the eye of the binary black hole mergers. This is bigger statement that I am making. So at each redshift in future you will be able to tell what is the basically total number of mass merger rate. You will also be able to tell at this particular redshift what is the mass distribution of the binary black hole that you expect, spin distribution, and that will be directly linked to your basically kind of dark matter evolution in the galaxies, etc. It can be linked, but we can discuss this later and see the opportunity that lies. So maybe in the last slide I can just talk about the Hubble parameter estimation after you combine all the results, right? Now that I mentioned, right, that we have many more events, so why to leave them? And it turns out that you see right now, again, this bright siren is the one that I showed you with the GW17-17. It had, in this case we knew the redshift very well because of electromagnetic counterpart, but if you do not but most of our detection are binary black holes. They do not have electromagnetic counterpart, so you do not know the redshift, kind of. But then if you assume that binary black hole mass spectrum, it's kind of a kind of invariant quantity across the cosmic times. Let's say the binary black hole, let's say the primary mass spectrum remains invariant against the redshifts, okay? Then right, in the source frame, if you know the binary black hole, if you know the primary mass black hole spectrum across the redshift, and your observed mass spectrum will be simply redshifted. So from there you can directly compute the redshift, because if you know the primary mass distribution, which is kind of constant throughout the redshift, is like frequency, right? Then Object frequency is related to the intrinsic frequency through redshift. Similarly, the object mass will be related to your intrinsic mass through redshift. So you can then infer redshift, and you already know GW. You already know the distance directly from the gravitational amplitudes. So then that method is called a spectral sirens. And dark sirens is completely different thing. It just tells you like, okay, you know from each event what is the distance posterior. Within distance posterior and the sky localization posterior, you can try to count all the galaxies, and you wait with the distance posterior which will be the more likely. And then, but it has certain, so all I am trying to say, having systems like GW17 or 70 is great, greater than great. But if you do not have it, it's not completely hopeless situation. We are not in the complete hopeless situation. We can try to get the H naught, and in the future when we have thousands of black holes, even this method, if you can keep on shrinking the uncertainty by simply accumulating the, of course by then, by the same time, if you have, let's say, 10 binary black hole, binary neutron star or some golden NSBS systems, that will be sufficient enough. So you see how exciting is going to be the future. Simply just by even just accumulating dark sirens or binary black hole, or just few binary neutron stars. It's just about time. What about the future? I just mentioned. Okay, so event catalogs, let's say in just 4 or 5 plus, which is going to happen, right? It's not something that is in the plan, but this is going to happen. So event catalogs will be like about 100 to 1000 detections per year in 5 plus. Population inference, of course, will allow you then, as I mentioned, right? If you simply just stack more and more events, you get better precise mass, spin rate, ratio evolution, and then you'll be able to test the formation much better, right? Uncertainty will reduce. So from the data you will be able to tell you this is the observed trends in the masses. Now it is on the theoreticians, can you explain this? Okay, but from the data side it will be very precise kind of in the future. And for the same matter, the strong field GR test, for example, in spiral measuring down. Okay, maybe I did not explain this, so just forget about it. So in the future, as Arun might have, I guess, discussed it, I was there in that part of the talk, you will have LIGO India, right? We'll have other detectors also. So then you will be able to also not just test, for example, just post-Newtonian structure of each polarization, but you will be able to also test if there are other polarizations. Some theory of gravity also predict extra, additional polarizations. And echoes also, which I did not discuss, maybe I can discuss in person. These are the late time, gravitational spectrum that we detect after QNM, after they have ring down, okay. And kind of, if you observe echoes, you are very close to saying that we have observed binary black hole. Well, we'll say, wait, you have been saying that we have detected binary black hole. No. Anyway, so next generation detectors, we have ET and CE, right? So we have Einstein Telescope, Cosmic Explorer. They expand our frequency bandwidth over which we will detect. For example, ET will go to slightly lower frequencies. Okay, that will improve our again the measurement for and the probes for binary neutron stars. Even for high mass binary black holes, because high mass binary black holes, the mergering downs basically happens at lower frequency, so that those events will be very precisely measured, and ring down structure, the Kerr nature will be very well probed in just the era of ET. If it happens, you don't need to go to LISA, just Einstein Telescope, and I think I'm not showing you, but Einstein Telescope will just completely and these are called third generation detector, Einstein Telescope, Cosmic Explorer. This will just simply revolutionize, because the horizon distance will go up to Z equals to the redshift equals to 50 at the time when the first stars might have just formed. You will be able to completely map the universe from the eyes of binary black hole or binary neutron star, basically. signals. And you might say that I've been just telling you things. Well, 200 years ago, you never would you have guessed that you would have known so much about the universe from the electromagnetic waves? No, right? I am just quoting the Kipthon statement. So I'm saying once you have the data, there is an opportunity to basically map that to your like understanding of your astrophysics and cosmology. And multi-band astrophysics, when you have these detectors, for example, ET and which is in like ground hertz to kilohertz, and LISA in millihertz, pulsar time in nanohertz, then you can do multi-band astrophysics. A particular, let's say, binary black hole system will spend, sometime in LISA, sometime in ET, okay, like that. And then if you combine the information throughout the evolution, you get more, you understand the system better, and all the probes basically improves correspondingly, right? For example, as maybe I couldn't mention the extreme mass ratio in spirals. I guess I'm sure that Arun mentioned about supermassive black hole bandit that could be detected by PTS, pulsar timing arrays, and of course cosmology and fundamental physics, right? I mentioned, just in this slide before I mentioned, so I'll just skip this. Just last slide, I will just end up here. I think this is my last slide. So the one thing that I did not I guess talk about is gravitational wave from core collapse supernovae, right? So right now our sensitivity, like any mass distribution in GR, if it is asymmetric, let's say it has developed quadrupole moment, right, it will emit gravitational waves. Now we already have like tools like we already detect, for example, neutrino that is emitted during basically this supernova process, right? Having any other probe would be just complementary, right? And then, for example, a gravitational wave produced during the core collapse will actually probe the mechanism of supernova explosion, dynamics of proton neutron star formation, early evolution. If you're not like if you're not catching my words, we can discuss after the talk, because I guess yeah, I'm sorry. So yes, so basically what I'm trying to say that the neutron star is the supernova process is not spherical, it's asymmetric, right? It's not symmetrical, so that will produce gravitational wave. If you can measure the detect gravitational waves, then it will give you a direct probe to how basically the let's say this neutron star, just before they became neutron star, they were proton neutron star, right? So basically what was happening at that time, for example, the deformed neutron stars basically will emit gravitational wave in G modes and F modes. These are basically F modes are fundamental modes. So you just like just let's say your neutron star, you deformed its crust, then it will become stable by emitting gravitational wave in F modes. So but each mode's calculation basically depends on the intrinsic physics. So you directly have access to basically your supernova process if you detect gravitational waves. The expected gravitational wave signature would be like short durations, 10 to 100 millisecond, unlike binary in spirals. I mentioned that for example slow mass in spiral binary could go up to hundreds of seconds, and the frequency spectrum would be broadband up to kilohertz also, okay. Yeah, it would be messy, but yeah, because it's not like simple, like kind of two binary black holes, orbiting nicely, and then you can predict nice waveforms. Here there is a lot of complicated physics that you have to account for. So it turns out that the signal is kind of very stochastic in nature, but it's not a noise signal. So you can distinguish it from the noise, and then once you can detect it, as I mentioned, it will direct give you access to what is happening just before neutron star is forming. The current detection prospects is that if you do a simple calculation, that our sensitivity, the current LIGO Virgo detection is just below 10 kiloparsec. So only galactic supernova can be detected. Gravitational waves from only galactic supernova can be detected, but these are very rare, extremely rare. You have to increase the sensitivity to get some finite probability of observing them, and that can only happen with third generation detectors like a Cosmic Explorer and Einstein telescope, which will extend this sensitivity reach to nearby galaxies up to few megaparsec, and I hope it will be possible to detect first gravitational from core collapse supernovae CCSN. Okay, thank you very much. I guess I'm sorry if I would have taken a lot of time, but
we are running a bit late time, so if you have any questions, we'll break for tea now. We'll have a short tea break. We'll resume
during the panel discussion.
Let's resume at 4 for the panel discussion.
Now we are going to go ahead with the panel discussion. The panelists today are Professor K.G. Arun, Professor Sriram, Professor Ajit, and Professor Manjari Bagchi. An introduction about Professor Manjari. She has been the faculty member at Institute of Mathematical Sciences, Chennai since 2014. She earned her PhD in 2007 from Jadavpur University, where she worked on quark stars. She then pursued postdoctoral research at TIFR in Mumbai, following West Virginia University in US, and also spent some time in IUCAA, ICTS, and the Institute of Space Sciences in Barcelona. Her research interests span gravitational-wave physics with pulsars, stellar dynamics, particularly in globular clusters, and the interior structure of neutron stars. She is also an active member of Indian Pulsar Timing Array, the International Pulsar Timing Array, and the Pulsar Science Working Group of Square Kilometer Array. Please join me in welcoming all our panelists.
Okay, welcome all of you in the last session of this event. Probably we could start with the questions from audience. I mean, you have heard throughout the day about gravitational wave astronomy and what drives it. We understand, like, you had some questions you couldn't ask, so probably this is the time for you to ask those questions, and then we can probably move to questions which you have, but you're not asking. Okay, so so please raise your hand. I'll bring you the mic. Any question that comes to your mind, something that you couldn't ask in the day. Okay, so probably we can come back again to them. And so I had a few questions noted down, which I said probably you also have those questions. Definitely I had. And I wanted to sort of start with that. So let me open my... All right. So we learned about a new astronomy almost 10 years back. It was being referred to as the dawn of gravitational wave astronomy. So it started 10 years back, but we were doing astronomy for over 200, or actually 400 years. No, this is Ajit actually. So he referred to 200 years or something. So that's what corrupted my thought process. But since Galileo pointed his telescopes, we have been doing astronomy, observational astronomy. Sorry, no, observational astronomy through instruments. So I had a question that how can we connect the gravitational wave astronomy with other traditional astronomies that we have? So actually I would like to hear from each of you, but maybe Manjari, you can start.
Yeah, I don't know why the mic came to me. So as I think I guess why mic came to me. So as Nidhi told, I work on pulsar timing array, which has detected low frequency nanohertz gravitational wave, but only the stochastic background. So it is quite interesting because LIGO succeeded only the single source events, although many events, but not continuous or background event, which they are still trying. On the other hand, PTA succeeded the background, but not the other types which we are trying. So in that way means pulsars are a kind of dead star, which he was mentioning, Ajit, that during supernova explosion, well, everyone talked a lot about neutron star. So neutron star, you have learned that they emit gravitational wave, right? But we do not detect neutron stars emitted by gravitational waves which are being emitted by neutron stars. We use the electromagnetic signal neutron stars are emitting. So like the electromagnetic signal from neutron stars are our say laser ray interferometer, very broad term. So obviously the astronomy we are doing means like our data can do a lot, like say you can measure neutron star mass equation, then population, how many neutron stars are there. Then to observe neutron star, you are building instruments, right? It's a radio telescopes you are building. You need to know radio astronomy. Then what else? Yes, like we detect the signals on Earth, right? The neutron star signals. So when they come very close, say electromagnetic signals from neutron star to Earth, sometimes they get, it's because in the galactic scale, our solar system is very compact. So the masses of all the planets affect. So we might think, okay, astronomy means exotic things like black hole, alternative theories of gravity. Even these days people are talking about extra-dimensional object or black holes from string theory. But even there are many things we can improve, even planetary astrophysics. Then these are radio signal. So you can observe a radio pulsar during daytime because telescope is just recording the signal. But if there is some solar storm or coronal mass ejection, you can detect that. So you can connect with solar physics. And then as you heard all this, I don't know, do they heard about constraining equation of state, right? Yeah, so like my PhD was neutron star equation of state. But that time it sounded so hopeless that probably we would never know, we will always play with thousands of equation of state. But now we can say something, right, from all this tidal deformability and neutron star. So I think it is very much connected, not only gravitational waves, astronomy, and other fields of like pure general relativity, classical mechanics, everything is, I think, interconnected. And doing this field is the most exciting thing because whatever physics you learn, you can apply. So that is what I would like to say, that everything is very much connected. So,
so Arun, do you want to?
Yeah, I can add, or you want to?
Yeah, you can add if you.
No, I think so. Just as to expand on what was said. So, what we know about astronomy until 10 years back is mostly from electromagnetic ways of observing, and therefore anything that we are newly inferring, if there is an inconsistency, that's something which should be understood, and that's what Ajit was also trying to stress. So there's no way of this different branches of astronomy cannot independently exist. They have to coexist, and there's a lot of give and take. And so just like how we have to learn basic astronomy and learn from the observations and how it tries to connect to what we do, similarly all traditional astronomers also will be trying to see where are the new branches of astronomy connecting the kind of problems they try to address. So, in the big picture, I think, we are like continuing from where we took off with the standard astronomy. It's just a new way. I mean, we shouldn't be, they're all astronomy, and we shouldn't think as this as a separate thing. So only one more brick in terms of the building block of the bigger thing. So it's quite natural that this is how we see.
Yeah, and we learned about one event, which was a classic example of multi-messenger astronomy, as we call it. Sriram, would you like to?
Yeah, I'd like to add a couple of remarks. In fact, there are differences in the details, but as Arun and Manjari emphasize, it's just another window to the universe. Many of the exercises you will do with light, you will do with gravitational waves. And in fact, in my talk, from a cosmological perspective, I try to emphasize how, you know, CMB provided you with a window to the universe, I mean early universe I'm talking about, and now gravitational waves will produce a window to the early universe. I talked about anisotropies in the cosmic microwave background. There is a gravitational wave background, stochastic gravitational wave background, and that will provide you, you know, that will have anisotropies in different directions in terms of strengths. So many of the analysis you can carry out. Of course, whether it is caused, the stochastic background is primordial, or whether it is happening because of black holes merging in the foreground. Well, as a cosmologist, it's a foreground. Much like, you know, synchrotron radiation from the galaxy is a foreground for CMB observers. So, I mean, I see that, you know, there will be eventually an effort to determine, you know, 2-point functions in terms of angles in the sky and their Fourier transforms, and similarly 3-point functions, etc., etc. So it is essentially a never-ending exercise in terms of astronomy, and many of the things you can, you know, do with optical astronomy, you can, I believe, repeat with gravitational wave astronomy.
Well, hello. No, yeah, I'm very loud anyway. Just starting. I don't need mic. No, well, for me, universe is just one, and the thing that we are seeing is part of universe. I mean, what do you mean? Like, we have to understand the universe as a whole, right? So, what do you mean? Like, I'm interested in EM part, seeing it through EM part. What do you mean? Like, but these are also part of universe. So, and for me, as Manji said, everything is connected. If you go deeper and deeper in the problem, everything is connected. You cannot just entangle the problem. Everything is connected. And I guess this is why I'm trying to stress in my talk. That it's, can you explain this? Because black holes are not just GR, abstract objects. It's astrophysical. It has to come through, your normal processes that you know. So explain it. So yeah, for me, it's just the part of the same universe, and we have to understand the universe as a whole.
Right. Yeah, and that's why I think we call them messengers. So there are different messengers, whether you're talking about optical messengers or gravitational wave messengers. I think that's the message that we... Neutrino is the next in waiting. Yes, that's the big news that is going to come to us. So I guess most of the audience here is either master's students or engineering students, undergrad students, or early PhD students. So I had this, what are the exciting things in gravitational wave physics that they can attempt, say 5 years? In theoretical gravitational waves, observational gravitational waves, and computational gravitational waves. So I would like to come to each of you. Arun, maybe you can start.
Start with the youngest guy.
Okay, Ajit, please. So what do you think the most they can start thinking about, and within 5 years it's going to be sort of big?
Well, so I think we are, at least if I restrict myself to the GW, gravitational astronomy, I think we are going to be in the era of data. We'll have lots of data, and we need to explain it. So in the GW side, now if you have data, basically, as from the beginning I've been trying to say, then it's like, I mean, I guess within 5 years is very kind of, I think, a tight window, but let's say next 10 years something, then I don't know, if let's say Einstein telescope comes in, or LIJA comes in, well, I think you are asking where they can contribute, is it?
Yeah, I'm saying what's going to be exciting in next 5 years, so that they can plan their PhDs accordingly.
Well, I think multi-messenger astronomy. It will be a huge achievement if we can really learn about neutron star interiors, equation of state, and if you can probe dark matter models, etc., using, let's say, gravitational lensing of gravitational waves, which I hope by the end of O5 we will start seeing. This is my understanding of the field of gravitational lensing. These are all the probes from gravitational waves, right? And why I'm saying this, because there are no accurate probes from other channels. That's why I'm saying that GW is very important for this thing, and that's why we are actively looking at it. So we'll have lots of data from unique sources. We'll have yeah, kind of, for example, as I mentioned, like, I mean, yeah, I think, like, I will be heavily interested in seeing gravitational from supernovae, quark collapse supernovae, so that we have some complementary information to that of neutrinos that we have been trying to detect using different things. And I guess if Arun can add to this, if the 3G detectors come in, I guess our calculation in this shows that we will be able to do it. So I guess, unless I'm forgetting things, I mean, this sounds easy in words, but they have huge astrophysical implications. Like really getting into the supernovae, like we do not know, right? As far as you know, right? So gravitational probe is really unique. I mean, so I mean, like neutron star systems. Neutron star equation of state. Thereby trying to understand the different layers of, like, the microphysics that go into modeling neutron stars, supernovae physics, gravitational lensing of gravitational waves, trying to probe the cores of area around the cores of galaxies. All those things are very exciting to me personally. Yeah, I'll just.
Yeah, so I think the bottom line I think Ajit is trying to convey is there's going to be a lot of data and there are a lot of new things that we can learn in next 5 years. Sriram, your take on what could we learn from the primordial gravitational waves?
So when young undergraduates or master students come and ask me, I tell 3 possibilities at this stage in physics. Either you should do biophysics, where there is a lot of experiments that are coming in. Quantum computation, it's just going through the roof. And the third possibility is clearly gravitational waves. Students come and say they want to do, some quantum field theory, quantum gravity, and so on. I encourage them strongly to examine, consider gravitational waves a possibility. There are infinite possibilities. Some Ajit has listed, and many probably we haven't even comprehended. And I think the data is going to overwhelm us. That is very clear. And it's going to tell us about astrophysical pathways to many phenomena, both on small scales and large scales, which the conventional electromagnetic observations may not be able to probe or may not even point to. From a cosmological perspective, there will be, all this, all of them are thinking from an astrophysical perspective, but there will be cosmological implications for all these observations. I mean, Manjari seems to believe that, what PTA have observed is probably SMBH. I would like to believe it's not. Okay, so there are many possibilities. In fact, I would say that there can be, if it is a stochastic, isotropic background, it can be cosmological. Of course, it can be astrophysical as well, if happens to be an isotropic distribution of supermassive black holes. There are many possibilities, and as I just indicated in the response to the first point, there are different ways of analyzing it. There are, if you look through the literature, there are many possibilities. For instance, are there deviations from general relativity, which Manjari mentioned, and whether gravitational waves are violate parity, which is something people are excited. All the theoreticians are excited about because they leave, signals which are which stick out literally, and therefore you can rule out theories which violate parity, etc., etc. So as I see, there are many, as a theoretician, trying to construct problems for students, there are virtually many possibilities related to the early universe I can think of, and and there are fundamental physics related to gravitational waves which remain unresolved. What will be the signatures at extremely high frequencies? People stuck to a very narrow window. They didn't go beyond a few tens of hertz. And if you look through the literature, there are detectors. People are talking about terahertz detectors, and you need to construct sources for them, and there are possibilities, electromagnetic, in the presence of magnetic fields, electromagnetic waves can be converted into gravitational waves, and they will occur at these frequencies. This is called the GZ effect. I forget the full forms of these names. So they're literally, as a theoretician, who has been working on primordial gravitational wave for the last 4 or 5 years, there are infinite possibilities, and it's a good opportunity for students to, consider it.
So you see, not only there is a lot of data, there are a lot of problems also to solve. Okay, so, and they go hand in hand as we, Arun, would you like to add?
Okay, so yeah, before going to nanohertz, I would like to start with Sriram's range, very high frequency, what usually people don't talk. So I think 2 years, no, actually it was last year, I was in a conference, it was a particle physics string theory conference. And I heard some talks that many of the string theory motivated evolution of universe, they predict very ultra high frequency gravitational wave. Maybe you can try about exploring those theories and making detectors. See, the lower frequency you go, your detector become difficult. You need larger and larger detectors. But in high frequency, you can do like bar, resonant bar. So probably you can involve, if some of you are interested in instrumentation, probably think of that. And there are, like this I mentioned about string theory motivated, but there are other, how many of you have heard Event Horizon Telescope? Okay, only one. So, okay, a few. So, Event Horizon Telescope from electromagnetic waves, they say that how will be matter and light be around the black hole. So, I know some people say that, okay, so that solution was from GR. But similarly, whether you can do from alternative theories of gravity, but they said no, this type of image would look exactly the same, but gravitational wave would look different. Then even within general relativity, there are things like which has event horizon, but not the mathematical singularity. We call them black hole mimicker. So they will give different types of gravitational waves, and that can be in every range, right? Like in LIGO range, you have stellar mass, then early in spiral in LISA range, and supermassive black hole in nanohertz range. So you can apply the same theory everywhere. And in nanohertz, there will be lots of opportunity. Probably you have heard about square kilometer array. Next generation radio telescope is coming. That is being built in a part in South Africa and a part in Australia. Australian part is not very useful for pulsar studies, that is very useful for cosmology study. But in the South African part, there will be square kilometer array based PTA, and that would probably make me. So I said that we failed to detect single source event and burst. So that would be possible. So if you, and there is big opportunity for India because India is full part of square kilometer array. It can be geographically in South Africa, but it does not matter. India has the equal right of South Africa and many other countries. So means what I would say, regardless of whether you are interested in theory or observation or data analysis or instrumentation, there are enough things to do.
Thank you, Manjari.
No, I think, yeah, I think people have told things already. Of course, gravitational waves, I should talk about LIGO India. I think those who are more experimentally oriented, there are a lot of opportunities for you to contribute, and this, if it's extremely important to make it achieve the kind of time scales and so on. But yeah, on other, I think, we are going to connect different scales. I think, for example, understanding growth of black holes. We are seeing billions of solar masses with JWST and maybe with nanohertz and so on. How did black holes grow from very low masses to that high mass? And we have no clue, and these are like a bigger problem which requires multiple ways of probing, and this could be an interesting problem. So there are many things, but and also one more thing I want to say about source modeling in gravitational waves, especially space-based missions are very time-bound, and we do not have waveforms for many of the systems we expect to see in LISA. So that's something theoretically minded people should be able to contribute. So there are, like Sriram said, there are many, to your interest, one can always find the many very interesting avenues to contribute.
I'll just give him a minute to fix this. I think this is the time we go back. Yes, but yeah. There's a question already. Yeah, why don't you ask me? Yeah. Just.
Actually, I have two questions. One is, what is the possibility that we are living inside a black hole? And second is, some scientists considered that quantum mechanics is total nonsense. Like one of the Nobel laureates has said, like Gerard Hooft, who won a Nobel Prize in 1999, he says quantum mechanics is total nonsense. So what are the takes on this?
Who would like to answer? I think any of you can answer. But
So you can define a horizon for cosmological space-times as well. So I don't know what people were referring to when they think they are inside a black hole. You can talk about a horizon, and a causally connected region. Maybe that they are referring to, and interpreting in this language causes some confusion about, what it implies. So there is nothing. I am not suggesting that we are inside a black hole. There is a causally connected region, which you can refer to as a horizon. You will, what is accessible and what is not accessible, you have to be clear about. So, about quantum mechanics, I'm not quite the expert on it. I will share what I believe I understand. Yes, there are open questions in quantum mechanics. Some understood, some not so well understood. And, why shouldn't quantum mechanics apply to this, glass of water when I throw it? It actually applies. In fact, people have applied quantum mechanics to the entire universe. So what is the domain of validity of quantum mechanics? Where does it fail? It's known, for relativistic system, you need to have quantum field theory and so on. For some mesoscopic systems, whether there are deviations from quantum mechanics, whether some of these deviations can help you understand something known as the measurement problem is quantum mechanics, which requires an additional classical system to carry out these measurements. I think these are open problems. So if you're quoting to Hooft, he's not talking about your everyday quantum mechanics where things seem to work well, and people are constructing quantum computers based on quantum mechanics. Okay, whether your pin will be secure or otherwise is based on how well they understand that. Okay, so I don't think they are referring to some violation of quantum mechanics in simple system, but in some systems where it is not, where they may expect to see deviations from it. And there are theories constructed which involve additional aspects which can lead to an explanation of something like the measurement problem, etc. So I think it is unfair to say that the quantum mechanics as a whole is going to fail. There are some parts of it, elements of it, which some additional things are needed in order to explain everything satisfactorily.
Yeah, I guess in science nothing ever fails. We just build on the previous knowledge.
It might be like that. See, general relativity is now true, right? But it does not mean that Newtonian gravity is totally incorrect, right? So we might get a superior quantum mechanical theory, but it does not mean quantum mechanical results are wrong, right?
Right. Anyone? Yes.
I just wanted to ask, is computational background now becoming as important as an astrophysicist? It's like, is it necessary for everyone who are interested in astrophysics has to have a computational background?
Probably I can.
Yeah, please.
So you can, what you mean by background, you can learn when you start your PhD. So like, and you never stop learn. Like my example means I learned only 50 marks on half a paper, only Fortran programming during my master's. Then during PhD I learned. And now I see my students, they don't know Fortran, they do coding in Python. So now I am learning at the age closing to 50, I'm semi-senior citizen, I'm learning. So computation, it is good. If your brain is logical, you can learn computation anytime. You don't need to be scared of. Computation is just logical thinking, right?
Yeah, as I said, background is one thing. So you will need, for doing anything that is worth in astronomy, especially driven by data, I think you will need to learn. But whether you need to do at the level when you enter PhD or you need to have at the BSc, it's up to different people or different background. It's true that if you want to contribute significantly to astrophysical research problems, you will need some level of computing for sure. And the level will vary depending upon what kind of problems you're working on. So computing is something which the earlier if you are working on a project, it's good to, the natural thing to learn. You should learn because it's something which is, it's an investment, it's a good investment in any case, not just in astronomy, but it's a good thing to learn in any case. But everything is driven by computing considerations these days.
Can I make a remark? They are being kind and politically correct. You need computing, simple. Whatever the problem you are examining in physics, you need computing. It is an additional tool, which you're going to make use of, and you will require, independent of what aspect of physics you are, or I believe, what aspect of engineering. Okay, so it is not something, there is a choice for you to learn. You are going to explore more complex problems, more difficult problems, explore a wider range of problems if you have that skill. It's like, this is a cricket mad country, it depends on whether you can play all the strokes. If you don't play some strokes, you're not going to do so well. So it's not a choice. You're better off learning it rather than, why don't you ask, do I need to learn classical mechanics, right? It's as simple as that. You got to learn it. You're better off learning it. You're going to attempt a wider range of problems and solve a wider range of problems, more difficult problems, solve them in different fashion if you have these tools.
Any other question?
What is the progress that has been made in measuring the polarization of the gravitational waves, because it is important aspect?
Yeah, I think, right now with the kind of detectors we have, we can measure only two polarization, but as we go to, I'm talking about ground-based LIGO type experiments, so as you go to more number of detectors, you have independent data sets, you can start, so you can ask the question that is there any evidence for anything that is not plus and cross? So that's it's a null test in the sense that you are looking for something beyond the two polarization. But as I said, when you have multiple detectors with 2 LIGOs, 3 LIGOs including LIGO India, Virgo and Kagra, you have 5-6 independent detectors, in which case you have independent data sets and you can start looking for specific modes, are there longitudinal modes are present and so on. So that requires independent, geographically well separated detectors taking data and having comparable quality data, because right now LIGO's sensitivity is much higher, Virgo is not that far. So you need like 5 detectors operating at comparable sensitivity and is taking data to ask these questions more precisely. But sooner we can ask this question, that whether is there any evidence for any extra modes of polarization, which might be easy to ask. You can see that LIGO papers are already asking questions about is data consistent with only only longitudinal modes and so on, which are not interesting questions. You can ask and answer, but they are not taking things forward. But first question I would like to ask is there any signature of anything that is not plus and cross? That we cannot do it right now, but sooner as we mature into a more sensitive era, we can answer these questions.
I mean,
Additional degree, beyond plus and cross.
Sir,
what happens is that, as I was trying to mention earlier, if there is a violation of parity where the polarization evolved differently, then the effects on the CMB stick out. I'm not able to comment about it. There is a concept called birefringent, which is extremely popular as we speak. There are many papers that are coming out. So detection of different types of polarization, if there is parity violation, there will be significantly different effects. In Einstein theory, both the polarization evolve effectively in the same manner. So unless there are polarization dependent effects, which I do not know whether it will occur in a coalescing binary, etc., okay, their strengths will be similar. You may measure them. There may be some angular dependence and so on, which I'm not able to comment about. But in the cosmological context, where if there is, there is parity violation, then the signatures stick out, and there is significant effort as we speak to understand, examine what are these effects of parity violation.
Sir, in PTA, pulsar timing arrays, I mean, the millisecond pulsars are used instead of normal pulsars. Why is there anything, why they are using millisecond pulsar in PTA?
It is just because millisecond pulsars are old and very stable, and slow pulsars. I mean, normal pulsars are young, they have lots of effect like glitch, star quake, so it is difficult to predict them. So it is just stability of the clock. It is just because of that.
So I have two questions, ma'am. We know that gravitational waves interact weakly with ordinary matter. So how does it interact with dark matter? Does it have any interaction at all?
Yes, it's weak, but there is an interaction, and you can compute the probability for it. And what we call, as I guess briefly mentioned in my talk, it's called lensing basically, or bending of light. So, I mean, this is the idea basically, to observe the effect of this dark matter on, I mean, not the individual particle, but as a whole, dark matter halos, they will bend the lights and form multiple images, etc. And if you can see those images, it's not just simple images like, of the original signal. There are some details that actually, details of the dark matter that is encoded in the signal. If you can observe those signals, you will be able to probe dark matter.
Okay. So the other question is, so the most acceptable theory for the creation of the universe is CMB theory. So, but other than it, there are some theories which are not, which does not have any unified proof or universal proof, but somehow they have. So, does gravitational waves also support the other theories? Because while talking in CMB theory, we support gravitational. We have a real proof for gravitational waves. In the early universe, it was formed, and then we can use it for the evolution of the universe, to observe the evolution of the universe. So in other theories, can we use gravitational waves, or is it any proof, or does other theories also support the gravitational waves?
So I don't know what you mean by other theories. Firstly, it's not a CMB theory. There are multiple points I would like to make. Firstly, we didn't talk about creation of the universe. We talked about creation of perturbations, inhomogeneities in the universe. The creation of the universe itself, yes, there are physical theories for them as well, but those are not well understood. And what are the observational predictions? It's not clear. So you have a Big Bang theory, okay? As I mentioned, general relativity is not able to explain what happened around the Big Bang. So your theory fails as it stands. So if you let go of Big Bang, what happened a little later. I mean, we believe we understand what happened from the epoch of inflation onwards, okay? And this is set in the hot Big Bang model, but that's just a name. As I indicated, I don't know what you're referring to as other theories. You can replace the Big Bang and by something known as a Big Bounce, for instance, okay? Yes, there will be gravitational waves generated in those scenarios as well. And they can have predictions too. Some of which may be consistent with the observation, some of them may not be. And they are being examined.
Hello. Yeah, so I have two questions that I want to ask. First is that I admit it is a lot of fun in the detections of gravitational waves and getting to know about the parameters of the systems involved, modeling waveforms, data analysis, and many more things. But where exactly are these studies going to lead us to? Maybe bigger detectors, precise calculations, or more detections? I would like to hear your opinion on this. And apart from that, the second question is, are there any particular event that we are expecting or hoping to detect which might completely change our view of our current understanding of astronomy and cosmology?
Ajit?
Of course, we are ready to experience such a moment. If any signal as such comes, we are eagerly waiting. I mean, but we already have bounds, right, on our expectation of such exotic signals, unless, of course, it comes from exotic objects such as, Arun can comment on boson stars or like gravis stars, etc. But of course, like there are two aspects of astronomy. First is, of course, improving the data quality, measurement, everything. Unless you do that, you cannot like precisely do anything, right? Physics, right? That is, of course, the direction. But other direction is about if you have a detector and it is capable of detecting things, then yes, we are eagerly waiting. Like for example, I also your question was completely changed the astrophysics. Like I'm not sure what you mean by that. Like for example, this signal from supernovae, like, right? If you detect it, is completely changed. I don't know that, but it will really help us understand the physics of the supernovae, which is very constant right now, very limited right now. So
on the other hand, as you were mentioning about the mass gap, if we have more like this grains black holes, what he showed, 80 and 100, and we say, okay, there is no pair instability, that might be some change what he's asking for.
All of these questions that I raised in my talk, if you were throughout the talk, I mean, all of these are pretty interesting for me. Like, if you are thinking about something else, maybe I'm not able to understand. Completely change means then, yeah, maybe if it comes from some exotic objects that are also theorized, by the way. So they exist in theory, like boson stars, gravis stars, all those models. People here can comment. But otherwise, it's like we are eagerly waiting to understand the system that are already like challenging for us to understand, like supernovae. How do you go from, let's say, stars to black hole? Right? This is open problem. Why don't we solve this?
Right. Yeah. I think I wanted to also communicate the sentiment there. It seems exciting, but it also seems boring.
Yeah, correct.
When you are continuously detecting binary black hole systems. So the question was that, is it going to be this boring always? I think Ajit has already answered part of the question. I think Arun had something to add.
So this is true that we are going to build larger catalog with a lot of diversity of sources. That's the hope. That's a compact binary angle. But what Ajit was mentioning about the supernova is a new kind of source which we have not seen and can enrich our understanding of astrophysics. And also, even continuous waves, right? Continuous waves, I think I got a question in the morning about, can isolated neutron stars emit? They can emit. Right now we can see only in our galaxy. We are searching for them. And, maybe in the next few years, we'll get an idea that will give us an understanding. That's an independent tool. So apart from building larger compact binary catalogs. We are looking for new sources of bursts like supernova and continuous wave emission from various sources, and stochastic. So we talk stochastic on both nanohertz and the cosmological scale. We also have a stochastic background due to unresolved sources of binary black holes in LIGO, which we hope to detect with O5 maybe with sensitivity. So there are different, yeah, I mean, there are, while the attention is right now on the compact binaries because we are detecting new classes of them, it doesn't mean that we are looking only for that. And so, in the next few years when these other detections come up, I hope they will also become more of a mainstream thing. It's quite unfortunate that continuous waves and other things are not in the mainstream, but, things may change. Yeah. Yeah, even maybe 5 years, I think, we are improving, because continuous waves are like sinusoidal waves, and you need to target them for longer and longer time. You get SNR over time. So this is something which can happen when it exceeds our threshold and so on. So we are indeed looking for more diverse classes and maybe exotic things. If you detect a compact binary which cannot agree with the black holes in the sense of no-hair conjecture, we are then probably seeing an exotic compact object which looks like a black hole, which we need to explain what kind of thing and so on. So it's we can keep on exotic thing. We can keep on asking what all we can see, but we need to wait. So we need to keep on taking data a very disciplined way and release our catalogs, do all possible analysis, and then see what comes up. And that's how I think this is going to proceed.
Yeah, please.
I think as more gravitational wave detectors become operational at a wider range of frequencies, I think you will have a continuum of data in about a decade or more. And, something I want to point out is that if you're talking about high frequencies, if you're, I talked about in terms of length scales and small scales and so on, you're talking about length scales. If I'm talking about something, a mode which leaves at the end of inflation, it is typically about 10 power 20 megaparsec inverse. And scales of the order of 10 power 22 megaparsec inverse essentially means you're talking about gravitational waves of length 1 meter. And there are talk about these are extremely high frequencies which will go into the gigahertz range in terms of frequencies and terahertz. And you're talking about experiments that are going to be carried out on a tabletop, 1 meter tabletop. So there are talks about such experiments. So I believe that in a decade or two, all right, there will be, much like electromagnetic waves, have been detected from one extreme in radio to the other extreme in gamma. There'll be gravitational waves observed, of course, depending on the phenomena and store and so on, or an extremely wide range of frequencies, and there will be enormous data coming in. You are in a certain period where you're observing these, because of the extreme, one sensitive telescope which is working today. As more telescopes become operational, you're going to have a multitude of data, an enormous amount of physics to explain.
Right, we'll just come after.
Hi, I actually have a question about this inflation. You said that actually have two questions, one about the inflation and one about the primordial black holes. The question about the primordial black holes is the process that led to the structure formation of the universe. Same should have led to the merger of these primordial black holes into a bigger and bigger black holes. So why do they still exist? And if you try to explain dark matter using them, because ultimately, like the structure formation, they all should merge together and form bigger and bigger black holes. And about the inflation, where did actually the inflaton field come from? Was it created at the instant of a Big Bang? If it was created at an instant of a Big Bang, why did the inflation not kick on earlier? Why later? And what happened to it after it has done its job, after the accelerated phase was done?
Answer the later question first. It's simpler. There are many scalar fields which can play the role of the inflaton. There are many of them. Okay, and there are single field models, two field models, etc. It comes down to how you perceive what is your high energy theory, and whether you want a phenomenological model or you want it to embed in a high energy theory, motivated by string theory, etc. There are enormous number of models, which I believe you should be able to pick one amongst these models which are consistent with the data and satisfies your theoretical prejudices and biases. I'm fairly sure of that. What happens post-inflation? Well, the energy from the inflaton is supposed to, be transferred to radiation, and there are people understand this mechanism fairly well. There are simple mechanisms called reheating. There are more complex mechanisms called preheating, and they are understood in terms of broad details. And people are trying to understand the microscopic physics of it and what are the signatures in the context of what it will be in the context of gravitational wave. Unfortunately, those domains, that's why cosmologists are excited, those domains you are not going to observe through any other means at small scales of, pristine physics through any other means other than gravitational waves. One just hopes that, as a cosmologist, that the astrophysical phenomena are so many and, so noisy that you're not able to remove them as foregrounds and observe some primordial gravitational waves. So astrophysical gravitational waves for a cosmologist is foreground for us, unwanted foreground. So people are trying to understand that. As far as black holes are concerned, I didn't quite understand your question. We are not talking about gravitational waves generated due to merging primary black holes. That is also a source. People have estimated those two. What I am saying is that, there was this question about whether these black holes that, which LIGO has observed, whether any of them could be primordial. If you ask that question and try to answer that, okay, from an inflationary point of view, what you end up are generating adequate amount of secondary gravitational waves. And strangely, they can fall in this window, which, can be in the nanograv window. And in fact, they seem to explain the nanograv data fairly well. Let me repeat that point. It is not the binary black holes are merging to form bigger black holes and therefore generating gravitational wave. No. The mechanism generates these black holes also generates during the epoch of radiation domination or during the epoch of reheating what are known as secondary gravitational waves. Okay, these are generated by the perturbations which generated the black holes themselves, not because of merging of black holes, and they can be what is possibly observed by the PTA. That's the proposal.
I have two questions actually. So here, during the gamma ray burst, the difference that are observed for a black hole and a neutron star collision is a gamma ray burst. What are the differences can be observed, sir?
You're talking about gamma ray burst produced due to a binary neutron star merger as opposed to a neutron star black hole merger.
Black hole merger.
Black hole merger won't produce anything, if in vacuum, so if the black hole is in free space, there is nothing, black hole would have accreted everything into it. So black hole merger wouldn't produce any electromagnetic signature unless it is in some, active galactic nuclei, like, there will be gas-rich medium outside from which either the component black holes or the remnant black hole can accrete and give you some light. So otherwise, gamma ray burst is not related to binary black hole mergers at all. And so that's a different story. But then you can ask, if you're asking whether binary neutron star merger based gamma ray burst and neutron star black hole based one, both of them can be there. Yeah.
No, sir. It's between the neutron star and the black hole merger, the difference is gamma ray burst. What are the differences can be observed?
I think that's a bit misleading. So it is. So I think what we try to say is that binary black hole merger cannot give you light, ideally, as I said. But the first binary neutron star merger, we had light also. That makes a complete, very clear distinction. It doesn't mean that every binary neutron star merger we detect will have a EM counterpart, because we detected at least two of them after that. Both of them did not have a kind of clear signature. So in terms of gravitational waves, only as Ajit was mentioning that binary neutron stars are low mass sources, they merge at high frequency, which means that they sweep through the band, 300, 3000 cycles and so on. So they are relatively longer signals in our band compared to binary black hole, which may be like a 0.1 second, a few cycles and so on. And in addition, as also Ajit mentioned, the tidal deformation of neutron stars induces further quadrupolar contribution to the wave, and therefore they have a very unique signature in the late stages when they come closer. They have unique imprints on the waveform. That means the waveform, if you plot a binary neutron star waveform waveform and the binary black hole waveform, they look sufficiently distinct. And that is how we estimate, if in the absence of light, we can estimate properties of neutron stars, including tidal deformability. That comes because of the additional signatures of equational state of the neutron star on the gravitational waveform. So that's how we distinguish. And light, the fact that we detected one even with light is of course an exception. It's not guaranteed at all. And that doesn't directly affect our inference purely based on gravitational waves.
Okay, sir, another question. Can there be an event where gravitational waves are produced equal and opposite that we cannot detect between two black holes?
What do you mean by equal and opposite? Because the gravitational, suppose you take a binary black hole merger, this is producing a quadrupolar pattern which is nearly isotropic. So from the source that is merging here, all throughout the sky signal is going out, right? And whatever signal is coming towards us, we detect them in the way. So there is no way of cancelling.
Another black hole merger that takes place the exact opposite.
No, I think it's not. No. We can have overlapping signals, as I mentioned. Two signals can come exactly there, and the challenge there would be to separating out the signals on the noisy data, which would require you to have models. So there is something different between the two black holes. For example, if everything is identical, one is coming from one patch of the sky, and other one is coming exactly from the opposite patch of the sky. This is a parameter that we fold into the analysis, and we should be able to separate these two black holes, even if they come on the data together. So by analyzing the data with appropriate thing, we can separate out these waves, and there's no way of cancelling one wave with another.
Any other question? So we are almost towards the end of the hour. So I actually had one question which I wanted to pose. If there are no other questions from the. Oh, okay.
So I'll not ask. Okay. So what is the most surprising result that we have found in last 10 years after detection of first event? Also, what have we not seen yet that we had expected? And also any bet for the next 10 or 15 years that we are going to observe? Like any bet that you can bet for the next 10 or 15 years that
he wants to make money. I don't know who wants to answer the question.
If you want me to bet on something, I think I will bet on lens signals. I think I'm very sure that by the end of 5 we are going to see lens signals. If my understanding of the calculations are correct, we are definitely going to see a lens signal by galaxy halos. I'm sorry, I mean, whichever falls in my expertise, but yes, you can remind me, I mean, like, as I said, like, if 3G detectors also come online, but you said within 10 years, right? I'm not sure within 10 years, then I would also bet on, supernova thing, but you said that within 10 years, so I'm not sure whether 3G detectors will be online by then. But I think Manjari can comment on the continuity of what is, like, the horizon distance right now, and like how it will improve, and then.
I think the first part, what surprised you in all of this?
Almost everything. Like, I mean, whatever notable events that basically, like, I discussed, right? I discussed just 4 or 5 events, not everything, right? And most favorite among those, I guess, GW17 or 17. Because I spent, I think, around 15 minutes discussing that event, right? I think because it gave, like, almost, it touches almost every aspect of, like, fundamental physics. I mean, I showed you, right? Every foundational principles of GR can be tested. Equation state you can find all these things. Like, what's better than that? I mean, I don't know, maybe if you're asking me about the last 10 years, that, of course, and then, of course, I guess, I think I'm also interested in detection of echoes, if you heard of it. That would be kind of a smoking gun for whether they are really black holes, or if not, then we can put very stringent bounds on what else it could be. Yeah, I'm also interested in QNMs and the detection of QNMs, precise detection of QNMs and echoes. Yeah.
I had to answer? Okay. No, I can
well,
answer.
I think the question was also about you didn't expect, but you detected, and so.
Yeah, I think, my favorite event is, of course, 17. There is no doubt about it. It doesn't come in. Yeah. I think, because, for me, I was told that gravitational waves are so rare, LIGO may not detect anything. This is what I've been told by regular astronomers all through my PhD. Even after first event itself was so surprising to me. I don't think anybody expected it to happen so soon. After that, everything was like, surprise, as was said. But 17 is very special, and I think it's just amazing. There is nothing that I think and seeing it unfolding in front of me over the 1 month is something which I will never forget in my life. In terms of other surprise, I think to me, the fact that nanohertz gravitational waves was something which I was told again that it will take years and years to do, but I think they don't call it a detection yet, but it's extremely important. It's a completely new band, and I was very, very happy and surprised that we could detect it in 2022, 23. And it's going to improve with all these things, so that again is going to be a completely new beast altogether, which we can combine with other things. So these are the two things.
I forgot about all those like final parsec problems, etc. Right? The evolution of supermassive black hole binaries, right? And now we have started seeing, right, the backgrounds from.
But that Sridhar will dispute is not, assuming it's a.
Yes. But
actually what Sriram mentions, so far the data means we have, so as Arun said, we call hint of low frequency because the detection is 3 sigma, and it is the standard practice to call it detection if it is over 5 sigma. So but this was this data was from various groups throughout the world separately, but now all the means North American data, Indian data, European data, means as I am talking here, our postdocs are adding, and on that, we are hoping by next summer, 26 summer, there will be more than 5 sigma detection, but this background low frequency, because we were working for a long time, I was not surprised at all, but I think now the data quality is being improved. Now there is something means we see the signature and there is a power law coefficient. If you can measure that, that can actually say whether it is cosmological or astrophysical. And quite interestingly, American data actually supports cosmological origin more, and European plus Indian joint data supports astrophysical origin more. So we need to redo our analysis again. And I expect that this was background, right? But like this but there are supermassive black hole in spirals. So I think within 10 years in low frequency regime, there will be single means inspiraling of supermassive black hole would be detected, and the merger of 2 supermassive black hole means burst with memory. So those I am very much interested to see in my lifetime.
Okay, are there any questions, last questions? So I have one. I actually wanted to sort of ask it at the end, but we are actually at the end. So if they want to go back home and want to start doing gravitational wave astronomy, what they should do?
Yeah, I think if at any point, take the first GR book that you can understand and read GR at the basic level. That's the first thing they should do. They should know GR well, and then understand the gravitational waves. That's the basic understanding. And if there are MSc students who are going to explore and so on, of course, they can try to do some internship where they do things. But I think nowadays, first you should have your own idea. You should learn GRI as a course or learn it by yourself. That would be the first step that I would suggest. But maybe I'm more curious to hear what Sriram says because he's more practical on these matters.
It's very simple. As Arun says, you start with a course on GR, what your favorite book. There are many of them. And do Magyar 1 and Magyar 2. He has 2 volumes of gravitational waves, and that should keep you occupied for a few years.
What about tonight? I mean, if they want to do some gravitational wave astronomy tonight, what they do?
Look, catch you? What do you mean?
No, guys, I'm off.
Some living reviews articles. So if you say living reviews on general relativity, so there will be lots of nice articles. Then about low frequency gravitational wave, it is in archive. So there you will find some very nice review article by Stephen Taylor. So there are lots of good articles to give you a glimpse before you start and learn all general relativity, and it is a very good idea to learn general relativity, and then obviously you can think about preparing for NET, GIST exams and start PhD.
Right, so there is no easy way, you will see. You have to go through the grill. What I wanted to sort of also ask is, can they perform a search? Going back home, can they perform a search? Taking the data is available publicly. Can they actually try this exercise?
Search with the signal?
Yeah, can they do some exercise of searching it?
Okay, you are asking, shifting towards data analysis kind of. Sure, there are a lot of tutorials available on Gravitational Open Science Center.
Right, so you can start today.
You can start today if you really understand the very, very basics of how even the Newtonian picture, okay, if you understand like how, let's say, binary compact objects evolve just at the level Newtonian, just assume that it is, a simple quadruple formula. I think just 2-3 lectures would be enough to give you a feel about like how binary compact objects evolve, blah blah merge, etc. And then you can start searching for it, right? There are of course tutorials that you have to go through, like what do you mean by SNR, what is noise, where even you can have fun. I think there are a lot of resources and those are simple, not public by LIGO-Virgo collaboration, if I understand correctly.
So
they can derive the chirp waveform.
Yes, you can derive the chirp waveform tonight. At the level of post-Newtonian, at least
Newtonian mechanics and the
quadruple formula you can derive. Believe me, that works well enough. If you are at the level of masters, right?
Right. So
this is how knowledge builds, right? You start with the 0 and then you can start searching. It will give you some feel also.
So if you want to get a feel for gravitational waves, you will actually find this data online, which is publicly available. You also have tools online, which you can use to search them, feel excited about it. And then if you're excited enough, pick the GR book and study it. Okay, so I think with this, we would like to close this. Okay, so sorry. So I'll go one by one. If you have any questions.
So I was just curious to gravitational wave, ask the gravitational wave astronomers whether, are you going to see a supernova in your backyard? Are you prepared to, with a waveform, is the signal going to be strong enough for you to detect it? When I mean backyard in your galaxy. And, are there some waveforms for other exotic objects in a similar fashion? Are we missing them otherwise?
As far as my understanding concerned, simple energetics can also be done for detection of, gravitational from supernovae. and based on that you can do the sensitivity calculation. It turns out that not before 3G detectors come.
Even within our own galaxy.
Yes, but it's very rare, right? Like I mean, yeah. Otherwise, you will be if it happens in our galaxy. Yeah,
so we are ready with the.
We are ready with
the waveform.
Yeah. I mean, there are simulations.
But what will be the duration of these signals?
Well, it will be very short duration. Right? Kind of
That's the point, right?
Yeah.
Whether you will end up missing it.
No, we have techniques, right? Burst-like signals, we can detect it.
We will not match filter it.
No, there are burst-like different. It's not like CBC type search pipeline. But if it happens in our galaxy, I think we are.
So, of course, we don't know. I mean, it depends upon the asymmetry of the supernova explosion, which is not known. But ideally, if our current understanding is correct, even without using any waveform, excess power techniques can detect gravitational waves in our galaxy. That's what you talked about. But the rates, of course, is rare. That's why the 3G detector thing will be required. So in terms of exotic compact objects, I think it depends upon how exotic they are. If you are looking for an object which are very similar to black holes with some parameter being different and so on, we can actually detect them. When we do GR test, one of the tests we do is for the black hole nature, and we ask the question whether Kerr hypothesis is correct, whether spin-induced quadrupole and octopole are they deviating from the GR value and so on. In that sense, we can detect them. We may not be kind of losing. But if it's too exotic, if there is a class of sources which are too exotic, then they may not be belonging to our class in the search itself. So that's so that we don't know. We cannot say without invoking a model which accounts for that exotic binary. We will be using them for sure.
So regarding the bet that was asked, why aren't we observing more neutron star or black hole neutron star mergers?
Because that is simply because they are low mass objects which we can see. So our horizon for binary neutron star is 150 megaparsec. And whereas black holes we can go up to redshift of 1 and so on. So it's simply the mass thing that we are, the fact that we can go very close by with binary neutron star, whereas we can go very large distance.
So it's not surprising that we haven't seen more of them?
No, it's not surprising. It's, so rates are being constrained. For example, at the end of the last observing run, the binary neutron star rate was very much, uncertain. But the fact that we did not see anything in the first half of the 4, and 1/3 has constrained it severely, so it has gone down. The upper limit has kind of gone down. It's not surprising given our understanding of that. It's simply the...
They are far away. It's not that GW17 or 17 is the only binary neutron that we have seen. 2 more binary neutrons parallel we have seen, but they are far away. They are from far away. So EM,
No, not only EM, there will be subthreshold. Even in our thing, it could be subthreshold. And so we have seen only 2 which are very confident ones. Second one did not have a GRB. They're all above the threshold, but there could be subthreshold ones, which means that they are lying outside. But the rates are not surprising. I think whatever rates we are, given the rates, it's not surprising that we have not seen anything yet. And of course, I think multi-messenger BNS next will be. It may take time, and kind of given where we are, because it has to be also pointed towards us if the GRB jet, etc. So it's going to be somewhat challenging. That's why we should look into other ways of doing Hubble constant measurements as well, like the dark sirens.
But as I mentioned in my talk, like even the dark sirens, if you have enough of them, like if you have just binary black holes, let's say few thousands of binary black holes, statistically they will start constraining, but even with NSBH, if you do not have, if you do not have EMS, like radiation is fine, because NSBH systems, so they can have large mass ratio, and so this large mass ratio enable detection of higher harmonics, and if you detect higher harmonics, this distance and inclination degeneracy gets broken. So they are our golden events for the future. If you see lot of NSBHs at higher SNR, let's say in 3G detector, not lots of, any regular NSBH will appear like that, if high SNR. So by the end of 10 NSBH, etc., we'll be able to constrain Hubble constant by sub%, even without EM counterpart, just because SNR is huge, SNR will be really large, and because of higher harmonics, the inclination and distance degeneracy will be broken, so we will be able to measure the distance, much more better, and then if you combine few of them, automatically, the calculation has been done. By the way.
Okay, so can I ask a question just now came? So see, when we talk about NSBH, usually we used to think, okay, neutron star would be around 1.5 and black hole say 15 or 20. So Q, what will be the mass ratio? But now with those high mass black holes, so are you people considering the Q means mass ratio, say lowest mass can be say 1 solar mass neutron star and 100 solar mass black hole? That is also physically possible, right? You cannot. So are you including such waveforms?
I think the paper that discusses goes up to mass ratio 6 or something. So that already
maybe I can say 1 and 60 or something.
Yeah, something. But if such a possibility exists, like 100 solar mass versus this, etc., that would be awesome. But rates will be very reduced, right?
Rates will be small also when there's asymmetry. The strength of the signal goes down because of the mass asymmetry. Because it's like a neutron star perturbing a large black hole. So you need some.
Very close by.
Yeah, so we need asymmetric systems to excite higher harmonics, but there should be not so high mass ratio that you don't even detect them.
Okay, 3G.
Yeah, 3G can detect anything.
Also decihertz maybe.
Yeah.
One question, sorry Chandra, last one. What is the status of departures from GR? Constraints on departures from GR?
Yeah, so I think we have done. Okay, now, so we have done various searches. So I think it's shown there are tens of 10, 15 ways in which we have looked for departures, and there is no evidence statistically. Yeah, so I think there's so that that's not showing any kind of deviation. That's on a single event basis, and on a cumulative event basis with GWTC4, which are still being analyzed at TC3, we have not seen any. So there is in summary, there is no hint of any statistically significant deviation from GR from what we have seen so far. So this will be GM by RC square of that is V square by C square will be like half, something like 0.2, 0.3.
Because the reason I'm asking is that Euclid will constrain, from the structure formation point of view, this growth function, and examine whether it will constrain whether there are departures from GR, and therefore you will have a wide range of curvature scales over which GR is constrained.
Yeah.
So these are rather model independent constraints. I mean, they are both in terms of the trajectories as well as the waveforms.
Yeah, I think the waveforms we are still using binary. Baseline model is the GR compact binary waveform, and we introduce deformation on various things looking for departure. So they are quite generic, I would say.
Okay.
I think if you see something that doesn't ensure that GR is violated, it could be systematics. But if you do not see anything, then it means it's a reasonably strong thing as of now.
So, any other questions? Okay, so then maybe we can, close the event. So thank you so much for joining us today. It's been
I'll be thanking you guys for joining here.
Yeah, and thank the speakers and the panelists for sort of presenting a very clean picture of what gravitational wave astronomy has been in past 10 years, the challenges as well as the scope of the field. So we hope to see you in the next event, and good evening.
now we are going to go ahead with the panel discussion. The